Okay, I think I'll go ahead and get started with just a few announcements this morning. First of all, thank you to everyone for an amazing session yesterday. Lots of great ideas, lots of integrating, which we're going to do a lot more of today. And so I'm really looking forward to seeing what else comes out. We have a few announcements. First of all, we're going to push the schedule a little bit today. Bob was originally going to do his charge to the workshop yesterday, which we ended up deferring to today. So we're actually going to flip, and he's going to do that right after I finish talking to you instead of at the end of the morning session. So we're going to push everything by about 15 or 20 minutes. So for announcements, the breakout slides will be up on the PowerPoints that we all put together will be up on the website shortly. I think Jen and Michelle are going to do that very soon. There's also a lost idea box that we now have in the corridor. So this is for if there's some idea that just didn't quite make it into the PowerPoints, or you have some idea that you would rather share anonymously or things like that. Let's make it an opportunity for discussion that didn't really get to happen yesterday. So please fill out anything that you would like to share and put it into the box. We also have 2 lost hotel keys, so if you happen to find those, let maybe someone down at the front desk know. There's going to be a photo this afternoon after the panel, or in the morning after the panel, sorry. Jen will tell us when the photo is, so just be ready. We're going to take a picture of everyone, okay? It's going to be out on the portico in the front. So today our breakout sessions are going to be on data-driven discovery across disciplines, so I'm really excited to see the integration that we can do. And Bob's going to come up and talk to us for a bit.
Thanks, Shauna. Boy, yesterday was so exciting for me, and I realized that one of the opportunities we have is to sort of think about this workshop as leading to some action items. And I didn't have a chance yesterday to tell you about those. So I want to sort of put this whole meeting in perspective to give you some history and also talk about some of the opportunities we have. So I am going to talk about the history. I'm going to look at some of the objectives that we might look at, and finally talk about these opportunities. The first thing I want to do is thank yous, though. We've really been fortunate. We've had major funding from the Alfred P. Sloan Foundation. NASA's come forward with a major grant to support travel for researchers, the Keck Foundation, the Gordon and Betty Moore Foundation, the United States Geological Survey, and we've had some wonderful collaborations with them recently. ELSI, the Earth Life Science Institute in Japan, and I'm so thrilled that there are a good number of people from the Japanese organization that played a major role in the thinking about how we put this workshop together. The Templeton Foundation, the International Union of Crystallography, supporting early career participant travel, and of course the Deep Carbon Observatory and the Carnegie Institution for Science. So I really want to thank these funders because we simply wouldn't be here without that support. I also want to thank the Senior Advisory Council. Many members of this, of course, have been participating already. They've provided a tremendous base of knowledge, experience, and inspiration for those of us who are working in this field. And please, if you haven't gotten to know some of these people, come up to them, look at their bios, and it's really inspirational that they've been able to help us and participate. Also, the workshop organizing committee. So this is where the really hard work has been done, and everyone on this committee is here, has been working. Again, thank them, see them, talk to them, find out some of their ideas, and I just have been so privileged to work with this diverse group. And finally, I have to give a tremendous shout out to Jennifer Mays and Michelle Hoon-Starr, who have done the heavy lifting of the logistics and organization. All of you have heard from them and interacted with them down at the front desk in terms of giving the presentations. You'll just see them around. And when you see them, please thank them. The whole DCO staff, Deep Carbon Observatory staff, has helped, but they in particular have had so many creative ideas, and much of, if there's any success at all of this workshop, it's in large measure thanks to their logistical support. So let's give them a big hand. I want to emphasize, and I should have done this yesterday, just as we all know, this is a time when we have to be very aware of respectful interactions with other people. So I like to read the workshop ethics statement. This is a statement that is both relevant for the Carnegie Institution for Science, any meeting that's held here, and for the Deep Carbon Observatory as well. So the organizers of the 4D workshop value the participation of every member of the community and want all participants to have an enjoyable and fulfilling experience. Accordingly, all participants are expected to show respect and courtesy to other participants throughout the event and in interactions online and associated with the event organizers are dedicated to providing a harassment-free experience for everyone. Okay, let me tell you some history. The roots of this workshop really extend back a little more than 10 years, and to a very similar workshop that was held in May of 2008. That workshop was sponsored by the Alfred P. Sloan Foundation, and it was in order to look at the needs and opportunities in what we call the deep carbon cycle, the idea of studying carbon from crust to core. We brought about 110 scientists, 12 countries from around the world. We discussed needs and opportunities. We had 4 parallel breakout sessions. We made PowerPoints on a template. Almost everything you see in terms of the structure of this meeting came out of that earlier meeting. And it really was very successful. The Sloan Foundation was impressed, and they said, we'd like you to do a program. And so we began the Deep Carbon Observatory in September of 2009. Major support from the Sloan Foundation. More than 1,000 scientists are now part of this from 50 countries around the world. We have, depending on how you count, leveraging about $500 million in resources, and this continues through the end of 2019. So this has been a really major program, a major success. Many people in this room are part. How many people here are DCO related? Raise your hands. Wow, see, that's fantastic. So this has led to a lot of things. So the idea, we had a mission statement. This is something we need to do for the 4D workshop. A mission statement, in this case, was to promote transformational understanding of the physical, chemical, and biological roles of carbon in Earth. So it's a lot of people. We have meetings, we have workshops, we have various kinds of exchanges around the world. One of the first things we did, and in retrospect, this was pretty smart, was to build instruments that didn't exist. We said, what are the scientific questions that are driving deep carbon studies? What can't we do right now? And so we developed more than a dozen new instruments very, very early on, invested in those, and that's producing huge results. I think the same thing may be true for us, but in terms of instruments, we're really talking about new analytical, new mathematical approaches, new data science approaches, and we need to be thinking very, very hard today and tomorrow about, are there various types of analytical and visualization approaches that might enhance our field but don't exist yet or need to be modified in some way. We also, at DCO, have over 150 field sites, and to me the analogy is data resources. We have hundreds of data resources around the world, but they're scattered, and I think we need to find a way of not consolidating them, but having both open access and some kind of integration so that they can talk to each other and we can use them seamlessly through various types of portals. So that's a real opportunity for us. The thing I'm proudest about the DCO is the early career community we've built. More than half of the scientists associated with DCO are early career, and there are a lot of early career scientists here who have been nurtured, I think, by that program. The opportunity, especially in data-driven discovery, is the future is the early career scientists now who, for whom data science is more or less second nature. And we really, anything we do going forward has to recognize the importance of making sure that community is nurtured and sustained. Please visit our website, deepcarbon.net. You can find a lot more about how this program, this large and well-established program, has sort of developed and give you a sense of the context of where we might go some years from now. The more immediate driver of this workshop was a very substantial grant from the Keck Foundation to a group of us, scientists who are at Harvard, at RPI, at Rutgers, Johns Hopkins, University of Arizona, and Carnegie. And together we developed what's called the Deep Time Data Infrastructure. That grant has now run its course, but it certainly is very influential. And what happened is that we reported, several of us, at a meeting of the Deep Carbon Observatory in St. Andrews, Scotland, back in March of 2017. This the work that we have been doing, I think, was sufficiently attractive to the Sloan Foundation that Paula Ozuski, who's one of the program officers, came up to me at that St. Andrews meeting and said, we'd like you to run another workshop. No guarantees that there's any big pot of money at the end of it, but we certainly think there's something exciting here and we want to explore it further. So that's why the Sloan Foundation approached us and said, let's see if we can do a workshop, and that's where we are today. Okay, our objectives. And every one of us would write these slightly differently, but for me, I see these large and growing Earth-based life science data resources. I see analytical and visualization methods that are incredibly powerful, and when you combine them together, I think they create what you might call an open access scientific instrument for discovery. And it's a very ecumenical resource because it means anyone, anywhere in the world who has a laptop and access to the internet can do great science as long as you make this open access and available. That's what we're trying to do. But we need an integrated approach, and I think that we can do much more than the starting point that the Keck Foundation allowed us to achieve. So this is my ambition. And so we need an action item. And the main action item of this workshop is going to be a white paper. It's going to be something that a subset of us write the first draft, but we're going to distribute it widely. We're going to get edits. We're going to get comments from anybody here who wants to have it. And then it becomes an open access document that you can use in a whole variety of ways. You can apply for grants. You can make research statements. You can use it other ways. I think we want to have multiple versions, probably a one-pager. You know, you want the elevator speech, but we also want to have a longer version, a substantial version. It could be the core of a proposal, as I say, and later on this morning we're going to have a funding panel where some of the key people that are funding this kind of research will tell us what they're looking for, but this is kind of the output. So that's the workshop organizing committee's responsibility to make the first draft, but everybody in this room has ownership of this document, and that's why we're doing these breakout sessions and so forth. Okay, I want to talk about opportunities. I want to end with opportunities because that's what I see in this workshop. I see incredible opportunities. They're just waiting for us to grasp them. And the opportunities are based on my conviction that data science and the data-driven approach has three pillars. All three have to be supported. The first one is you have to have questions, really profound and exciting questions that drive what we do. That's the motivation for all of us as scientists. But then you need to have data resources, and we need to create them, we need to enhance them. This is part of the challenge and the opportunity that we all have, building data resources and sustaining them. And then we have to develop and implement methods of data analysis and visualization. If we put these three pieces together in a creative, original way, we have something really, really exciting. So let's talk about these opportunities, database development, and here I want to give a shout out to some of my heroes in this field. The Rough database, and I'm just going to talk about Earth Materials here, but there's many other people who are doing this. But Josh and Alex have been amazing working with Bob Downs at Arizona. Jalian Ralph and building a crowdsourced database unlike any other I've ever seen. It's an amazing history and experience. We have Kirsten Leonard, who we heard yesterday, EarthChem and IETA. Shannon Peters worked with MacroStrat and also has worked with PaleoBioDB, and Drew Macenti, Mike Meyer, who are here, who are working specifically to build that Precambrian aspect of the PaleoBioDB. These are people who have really dedicated themselves to providing an open access community resource. So what are the opportunities? We need to still recover this long tail, this dark data that's out there. There's vast amounts of data which we have an opportunity to find and add to data resources, but they don't exist yet. We need to change that culture of data sharing, so especially in fields where they're sample-oriented, where people hold on to their samples and hold on to the data. We need to change that culture, and the early career community is where that's going to happen. We need to establish long-term stability for data resources that is a stable platform. We don't want to have the server for some critical data resource in somebody's bedroom, as was true for Mark Iorso's great database recently. Meet Mark if you haven't already. And I think we need to celebrate, and we need to fund scientists who create these data resources. So this is a great opportunity for us and something we can do as a community. Okay, promoting change. I think this is one of the things I really want to see happen. And let me tell you a story. I could talk about any one of a number of fields in earth science and earth materials that I'm familiar with, but last week we had a very famous geochemist give a seminar at the Carnegie Institution. And it used to be 40, 50 years ago, it maybe takes a week of work to get a data point on a single isotope or a single element that's a trace element. But now you have machines that generate 30, 40 elements at a time, dozens of isotopes. I mean, this is automated. You can run hundreds of samples in a week. And so what geochemists do is they often measure these isotopes or trace elements in order to understand a big question. How did the crust form? How did the core form? What was the timing of these events? And so you're talking about very complicated problems in 4 dimensions, 3 spatial and the time dimension going on. But still, it is a traditional thing to use an XY plot, for example, the slope of a line to say this is how the crust formed or when it formed. Or even use something called a Caltech plot, which is plotting something against nothing. It's called that because back in the early days of geochemistry, Jerry Wasserberg, just a brilliant leader in this field, producing a data point. Sometimes it took a long time to get one data point. So you have an x-axis and then just a whole series of samples. Okay, well that's great for 50 years ago, but it's still being done that way. Here's an opportunity for us to try to change this culture. I had an email exchange after the seminar and asked, is there a way to use all the data to understand the complex problem? And the answer was no, it's fallen out of favor doing multidimensional scaling. And just think, if you threw the whole incompatible trace element data for an Earth system into a multidimensional analysis, you would end up with a meaningless average of the processes involved as the different elements are tracking different processes occurring at different times. Isn't that the point? I mean, isn't that what we want? But there is, there's a cultural resistance here. So we need to be able to come up with the analytical methods to show how powerful it is to use all the data and not just XY plots. Now, I think that there's a huge opportunity just waiting for us. An opportunity is funding. And later today, we're going to have representatives of government agencies and private foundations. We also need to make sure that our own institutions place priority on data science in hiring and tenure and promotion decisions and so forth. That this is a really tremendous opportunity for departments. And I guarantee you that in 10 years, every geoscience and bioscience in the country that doesn't have someone who does high-level data science will. It's going to be essential that we teach every student the coding and the skills necessary to do this. And note to funders, incredible opportunity here, as I'm sure you already know, but I think that this community that you see in front of us really can do this. New math and new data science. I think one of the really exciting things that I'm realizing talking to my data science colleagues is that what we're doing here is not big data. You notice we haven't used the term big data. What we're doing is small data. It's sparse data. There's 5,000 minerals. There's 10,000 stromatolites. We're looking at 4,000 planets. This is something where we need new mathematical tools. We need new ways of analyzing data, perhaps learning some lessons from big data, but really having different. How many people here would call themselves mathematicians? I know Greta's here, or a few of you. We need you. This is incredibly important, and I think that we should all recognize that data science and applied mathematics is not just a tool that we can apply, but this is a vibrant area of research in its own right, and that we need to partner with the mathematicians, the data analytics people, because we will learn from them, they will learn from us, and together we can advance our own disciplines. If you're not opportunistic in this field, you're missing the boat. And opportunism is a good word. Advancing your own career, but advancing it by collaborating with people who have complementary interests and skills is a tremendous point. So I think this is a tremendous opportunity for the data science community. So, as a community, and that's what we're trying to build here. We can define a new set of integrating questions. We can foster a community of like-minded scientists. We can work together to develop that culture of open access data methods. We can raise money. And let's not be coy about this. Money drives ventures like this. It's really important to provide the glue to community and provide an incentive to work. So I want to conclude. I've been doing science for a long time. I've seen a lot of different programs. I've shifted my own research interests from time to time. I've never seen a more gifted group of scientists. This room is just jaw-droppingly awesome to me. I've never seen a more compelling constellation of scientific questions. And the premise for a great research program is in front of us. So I say, let's seize that brass ring. Let's band together. Let's make some history. With that, I thank you. I'm really looking forward to this morning's session. Here's what we need to do, build a network. And thank you very much. And now it's my pleasure to introduce Ahmed Elish. Ahmed's a graduate student at the Rensselaer Polytechnic Institute working with Peter Fox. For 4 years, he worked with Oracle in its Egyptian office, so he's got some real industry experience as well, and he's been an inspiring early career scientist to work with, has made tremendous advances and helped us in many, many different ways. So Ahmed will chair the next session on data-driven discovery in the data sciences.
Thank you, Bob. Good morning, and thank you for being here. Our first speaker, Dr. Peter Fox, is Tetherless World Constellation Chair and Professor of Earth Science, Computer Science, and Cognitive Science at Rensselaer Polytechnic Institute. He is the Director of the Information Technology and Web Science Program at RPI. Before RPI, he was Chief Computational Scientist at the High Altitude Observatory of the National Center for Atmospheric Research. Before that, he was research scientist at Yale University. Dr. Fox earned his PhD from Monash University in Applied Mathematics. His work encompasses the areas of data science and analytics, ocean and environmental informatics, the semantic web, and solar terrestrial physics, among others. Please welcome my mentor, Dr. Fox.
G'day, how you going? Thanks Ahmed, and thanks Bob, because you sort of gave a part of my talk, so I think that's always fantastic. My charge here this morning is to step back a little bit for the data science side of the opportunities in data-driven discovery. So data-driven discovery is the theme of the workshop, but underlying it, you've heard a lot about data science so far. And I've got, it's not going to be a long talk and terribly involved, but I want to just sort of frame some of the things that we've done that have influenced, I think, some of the tremendous science results that you've seen. And the first thing is to get the slides to move forward, which I should know how to do. Yeah, keyboard. Yeah, let's do it that way. That's good. All right, no worries. I've been at RPI 10 years, and one of the things I got to do when I went there was to create a new curriculum. I could teach whatever I wanted, and I decided, I'm going to teach data science. And the first thing I needed to do was unpack and hopefully disambiguate what data science really was, and in fact, to unpack this particular diagram that sits before you. And it's a diagram that many people maybe have seen before and has been falsely cast as the data to information to knowledge sort of linear progression. And when that was first conceived, it seemed sort of sensible, but it's totally wrong. It's totally wrong because, and I think Shannon gave a tremendous example of this, at play in the world we deal with today, we have data, we have information, and we have knowledge, but often knowledge, things that are in papers, for example, but can become informational resources like word clouds. But they can also become data. They can become structured resources. And there's many important things about this diagram. I teach this, I usually spend half an hour on this diagram alone. I'm not going to do that today. But by now you've stared at it a little while, and hopefully you've noticed the big green circle here called context. And the attributes that go with data, information, and knowledge really constitute what we might otherwise call annotations or metadata that goes with each of these designations. And overlaying this in an ideal world, and there are some communities that have this producer and consumer community that intersect, like I've drawn here, but many fields of endeavour, the producer communities and the consumer communities are very, very widely separated. And you can already maybe start to see in data science especially, we have a lot of circumstances where you as a consumer, i.e. a data scientist, doing science with somebody else's data, are very far separated from those who produced it. And this has really important consequences for how you do data science. And it came up in a breakout yesterday. You know, data quality is one of them, fitness for use, there's a variety of different things. So in doing data science, we view this entire landscape as an ecosystem of data, information, and knowledge and all the attributes that go with it. And we use that ecosystem as a metaphor, not as a sort of a literal meaning of ecosystem. All right, so I thought, all right, how do I think about data science and data scientists? Drew Conway is famous for producing this diagram on the left-hand side here. And it attempts to show the intersecting skill areas and domain areas that constitute a data scientist. So you have hacking skills, you know, we would probably call them programming or coding capabilities, math and statistics skills, and substantive expertise. And for a room like this, substantive expertise could be a single domain, but many of you, when you introduce yourself, are across multiple domains. And you can see the pairwise interactions between hacking and math and statistics. And you can see where traditional research shows up, and that's what I really like about this diagram, is that data science is part of an ecosystem that does not exclude traditional ways of doing business, hypothesis-driven, inductive, deductive, and so on. But the intent is that data science is really at the core. And when I give talks about this, what I have been led to is to use, again, another metaphor, which is the idea of anatomy and physiology of the human body. So anatomy is individual body parts, organs and so on that have a particular function, and physiology is the assembly of those pieces of anatomy into a whole. And I believe it's a good way to think about data science and data scientists. And so if you were to draw some arrows between anatomy, the individual functioning pieces, then obviously you can point to a number of components here. And if you were to draw the physiology to me, the combination of all the functioning is data science, as well as the whole intersection. Now you'll notice there's a really important intersection here, which is called the danger zone. And the danger zone, I think, is one of the biggest challenges for data science today. And I attribute it to a piece of missing anatomy. In other words, there's certain functions that people who potentially go off on their own and think, well, I'm going to just download this package and get this data set and I'm going to produce results. And it turns out to be garbage. And it introduces a level of mistrust and disrespect in the community that we have to be cautious of, because it's part of science. That happens from time to time, but there are well-established ways for it not to happen. Now, as a result of this anatomy and physiology approach that I take, what I do when I teach data science and sort of bring forward some of the, I'll show you a picture of all the folks that from RPI that are here today. I think about it very much as what should people do as an individual, and so you can see a list of things here. This comes out of the learning objectives for the courses that I teach. And it's important, data and handling data and treating data as second nature, just like you would run an instrument or write a piece of simulation code. It has to be built in to the people that we're educating. Now, of course, we've got a challenge because we have many experienced people out there that have not had this path. But I believe it's within many people in this room and outside this room to establish these individual functions as an individual. And then the physiology piece of this is often a group. There are relatively few individuals that have the anatomy combined in the physiology to do data science, quote, by themselves. And you know, you can see it's a well-rounded set of capabilities here, presenting conclusions, presenting analyses, finding and integrating data sets. So data science really is a socio-technical system. The title of this talk is about techniques. And techniques are not just algorithms and pieces of software. Technical is also organizational. So here's, you might recognize some faces. Here's Shauna and Ahmed and Feifei and Fang. This is the ground floor of the Winslow building, the oldest building on the RPI campus. And it's about a socio-technical system. It's about bringing people together for a common purpose. And, you know, we use extremely sophisticated techniques such as drawing on whiteboards and creating matrices of, and this is real live from the Keck project, things that we have to do, ideas, and then analytic techniques, both visual and quantitative techniques. And the objective is if you don't have that entire matrix filled in by the time I get back, you're in trouble. And people like Mike Meyer, you know, were capturing these, and it's a way of organizing and demonstrating progress, and people sort of self-allocating and forming in groups and exercising that physiology of doing data science. Next, I want to just tell you that dimensionality, you'll see this a lot, the curse of dimensionality. Dimensionality is not a curse, and Bob set this up very nicely. I say when we do data science, we are dragging people out of 2 dimensions. I mean, literally dragging, kicking, and screaming. And so on the left here is a multi-dimensional scaling of minerals from an igneous rock database, brought down from 51 dimensions. You've seen this iconic diagram of the carbon bipartite mineral diagram many times. This comes from 17-dimensional data set. And what we do is we're able to encode a lot of the dimensions in these visual representations, and the interaction with the domain experts takes a little bit of time because like they've not really seen these renderings before. And you have to be patient and spend time, but getting them access to multi-dimensions is really important. And you've heard integration a fair amount too. And in the Keck project in particular, we sort of diverted directly to an infrastructure, and the infrastructure is also people. It's not just a computational infrastructure. And you have to support this dimensional integration in many dimensions, and it's a multi-type, it's a very heterogeneous type of integration problem, which is people find often very challenging. And integration is not just what we would think of the classical integration, you integrate in spatial terms, or time, because often we don't have time, and the damn planet has moved around. It's just things aren't in the location that they were when we're studying them. So you have to think about other ways of integration. And someone might have said this yesterday, in data science and multidimensional representations, there's actually no such thing as metadata. It's actually all data. And this is a very significant challenge because sometimes the metadata is categorical, sometimes ordinal data. And we can deal with that with advanced data science techniques. And so what it means is you've got these diverse data resources and people ask you, well, what single format can we use? Well, forget that. And I think Kirsten mentioned this yesterday. Keep your own data formats. What we do is we bring it all together in a graph representation that supports the heterogeneity. And logically, when you've got a graph, this hop, skip, and a jump to a network, which you've heard quite a bit about at this meeting, is one way to work with that graph. And I think, again, Shannon mentioned this, the data structures are extraordinarily important, getting data into the right form so that you can use them in the common open source packages. But scientific equivalence and making sure that you're getting faithful representations, preserving that through the data analysis pipeline is critical, as well as the origins, the provenance from where things come. And personally, you know, I've spent my entire career jumping around across many disciplines, and I think it's a frontier, certainly a frontier for data science, breaking out of the single discipline, like I'm going to help you predict stock market prices, is only good so far. You know, I'm interested in the origin and the fate of the planet and things like that. And what that means is, by using this graph approach and network approach, we can think about multi-layer networks, correspondences between things that otherwise we would not necessarily be able to render. Bob set this up nicely. Okay, big is, you know, when you have big, it's great, but the real interesting things for data scientists is the sparseness, the heterogeneity, and the small data. And this has been mentioned a number of times. I'd love it if you went and read a paper that I wrote with Jim Hendler a few years ago on the science of data science. And there's many elements in there that describe where we need to go with data science, because you have to make your problems, or you have to let the data scientists make your problems relevant to them as well. This is absolutely an equal exchange. It's not the IT person who's going to come in and do some coding for you. If you want that person, that's not the sort of person that you'll find in this room. Part of the socio-technical system of data science is this information space that was in the middle of that ecosystem before. The information space is where humans consume and start to have the conversation that eventually leads to understanding. And so having visualizations that have some dynamic nature to them. Have you seen that before? Oh, look at that. You know, this is a chord diagram, which is one flat representation of co-occurrence. And it's a chord diagram that represents potentially an evolution of co-occurrence of certain types of minerals over Earth history, right? So that's pretty cool. The skyline diagram now you'll all be completely hypnotized by. There's a secret message in there that means you need to send me your credit card information at some at some point. But I just want to emphasize, the skyline diagram was generated by Stefan Zednik, who's a senior software engineer. He generated it in the matter of like 2 or 3 days when Bob said, I've got all these individual locality data for each of the transition row elements, and as a function of 4 billion years here. So this is, you know, the availability of metals and their isotopes over the entire Earth history, and it goes into proteins and all these different things. And Stefan said, oh yeah, I can do that. And in a couple of days, he did that using pandas in Python. And it's become, you know, an irreplaceable representation. So visual techniques to render all of the data that we have available is part of data science, and doing it in innovative ways. In addition, the chord diagrams, in addition to being often very dense and hard to understand, you know, can be interactive, so that you can go to a particular place on the chord, pick a particular mineral, and look at its co-occurrence network interactively. And that gives insight, so you can move around and find out the types of co-occurrence connections in an otherwise very complex space. Drew showed the Ediacaran assemblage networks, you know, extinction events, and Drew made this conclusion. So this whole idea of data-driven discovery, rendering in a network, is like, oh, there's an extinction event there. And that ends up with a science hypothesis, which you then go off and further take a look at. In terms of other visual representations, taking these networks into multiple dimensions, 3 in particular, but also virtual reality, is really essential. And now, you know, you're taking a look at this. This is a movie recording of one of our team actually navigating through this. This is Anirudh Prabhu's representation, and it takes a little while to figure out what are you really looking at, and spending time and looking at what's being represented. So, and then here's a bipartite network where the grey represents locations, and so the locations are sort of clustered in the centre, and you see the periphery, and the colours mean something, and you need to change the colours that represent other data. It's not just a node that's arbitrarily coloured. You can just probably now imagine the virtual reality rendering of this. And Drew showed this as well. You know, fantastic result, right? Implied time axes, extinction events, these pinch points in the network. But also on the bottom left is more of a stylized representation, which highlights in a coloured way the clustering. Major structure, the overall clustering, the red, the green and the blue, which I'm sorry is reversed colours from what's on the right. But then within the clusters, there are clusters within clusters and represent things like minor extinctions, radiation events within a particular epoch of Earth history. So overall, the way in which we think about this from a data science infrastructure point of view looks a little bit like this architecture diagram, and this is my second last slide. The data resources are absolutely essential. The middle layer is often where many communities stop. They do statistical analysis, they do modeling, they do other sorts of analytic models, and it might be based on maybe one of the resources, maybe two. But the whole idea behind an data science infrastructure is you have access to a lot of these resources, but it's really the top layer of this. Discovery visualizations, analytics and mining, and building out for us. This was the diagram that the Keck Foundation said, yeah, well, let's go ahead and do that. And we're building out this global graph of the D-time evolution of the planet. So then you have to ask, what's in it for data scientists? The major thing, I think Kirsten, someone mentioned this, a bunch of people, the 80-20 rule, you spend 80% of your time getting the data in the right format. Data scientists want to reverse that and make it 20% of the time and 80% doing science in an interactive sense. And we want to convey that coding doesn't hurt. Mark Giosso, you could hit him up for a cap that says "Make America Code Again." And it's true, young people coming through are not afraid of using Python and using R and so on. And we do need some new things, new ways of thinking about significance tests, importance criteria, interpretation, i.e. we need to think about more anatomy and physiology for data scientists. We need data management to be routine. And I just want to say, for people who deal with industry, open data is good, but it's not essential. And Anirudh Prabhu, who will give you a long discourse on this, it's the open algorithms, not so much just the code, but the way in which you think about working with the data that needs to be open, because that's basically the scientific method that you're using in data science. So just keep that in mind. And here are the folks, current and past. Many of the people are at this meeting. Won't go through all the names, but just so you recognize them. And you know, these people are computer scientists, informaticians, and data scientists. And it's an example of one group. And there are a number of groups in the US and around the world that would readily be engaged or are engaged in a community like this. So I hope I've given you a little flavor for how data science might come together for data-driven discovery. Thank you.
Questions? Questions?
It's on.
It is.
Yep.
I have two comments. One of them I think, Peter, will be to you, my second comment. After thinking through this really exciting set of presentations and discussions yesterday, sleeping on it, getting up, having breakfast, I think a draft theme we might think about for this white paper is the origin of planetary systems, habitability, and life. And to do that, you need to go from the exploding data for Earth, for the solar system, out to exoplanets, and try to put everything together. But to me, what's the key stumbling block? If you go 3 slides back, forward, so you have your configuration diagram with the horizontal bars.
Oh, I'm sorry, the layer diagram.
Yeah.
That one.
So I work in the planetary data system, and that's a distributed system, and unfortunately, each of the discipline nodes has a different interface. We use the same common formats, but it's difficult even for me to be able to pull things out of, say, the plasma site versus the atmosphere site. So if we look at other parts of the solar system, the Earth Observing System, Data and Information System is distributed. There are dozens of interfaces. They use the same format, different than the PDS, but it's still very difficult for me, and I do this, to get what I need. And then if we look at astronomy, it usually fits. And again, it's a different interface, it's a different format. This is not unlike, all the languages that are spoken on Earth. And you're not going to get the French to decide to speak German. And you're not going to get all the databases to be consistent in terms of the interface and the formats. To me, the key stumbling block to meet this kind of draft vision is how we access data in a more translational and transparent way for users, so you're not spending most of your time trying to figure out, how do you translate this format to another format that I can use, and how do you actually get through the interfaces that are all different. So, and it's a challenge, I think, to data scientists. How do we solve this? I mean, is it the equivalent of having your little iPad and translating from French to German? Or is this an impossible task and we have to spend most of our time trying to figure out what is the structure of the database, what is the format of the database, how do I get through this OCT2 interface? That to me is a stumbling block because data-driven discovery by definition needs data.
Would you like to come work for me? Because this, I went through this architecture diagram a little quickly. I sort of wanted for a representation, but the the resolution of your stumbling block is in grey. The grey layers are the mediation layers. Then we basically had to solve this problem for the virtual observatory, starting in astronomy and in geophysics. Oh my gosh, 15 years ago, and it's the mediation layer. And the mediation is not just at the scientific level, but it's at the format level. And actually, you've prompted me to remind me that these orange arrows at the bottom here should not actually look all the same, because it gives the impression that there's a uniform interface. But as you said, that's completely not true. And this is where graph representations really are important. And the little triples, the little triangles here, the sort of a semantic representation, is the fundamental way in which we absolutely solve exactly that problem. So we've got a good handle on it. In geosciences especially, there's a wave towards, quote, linking data together and not being overly obsessed about individual formats. And the reason you can't be is because you have data repositories, you have scientists, you have data managers who have to retain their own format because it's the one that they've not just worked with for years, but they've chosen it for a really, really good reason. You don't want to try and do a sort of a raw format conversion. You want to do this translation. And the same translation occurs at the upper level when you go to these more integrated applications. So application level integration and mediation is fundamentally a part of the infrastructure. Now, if you want to get involved in that, that's good, but I don't want you to know the details of the grey, because that gets in the way of you doing your science and doing the things that are really important. So, Janet?
Hi, Peter. That was great. Thank you. There's a lot to follow up on, but I just had just a couple of things. Your distinction between producers and consumers was spot on. And I think for a large fraction of the data that's relevant to deep time in particular, that conflict or poema, I guess, is established because of the difficulties currently involved in creating synthetic data sets that are required to address questions like you can address with the paleobiology database. I want to stress very clearly again, if it didn't come across in my presentation, that we are literally on the cusp of greatly eliminating that barrier.
Yeah.
And you suggested that we don't have big data problems. We do have big data. There are millions of illustrations, who knows, of untold number of fossil specimens that we currently take zero advantage of. Not to mention the terabytes probably worth of other associated data represented in images and tables and textual descriptions of things that have been collected at great cost and effort over decades or longer in the field. What we lack is an ability to take advantage of this big data. And this is, to me, the exciting opportunity that's staring at us right now in this domain, is we have the ability to transform the way we think about data sets for synthesis-related problems in the Earth's deep time life sciences. And it's exciting to be at this point. It's also frustrating because we see these different directions pulling in ways to tackle this problem. Some of them involving, new approaches to managing the flow of data when it's acquired. And Kirsten and Brooks talked about maybe making progress on new data that's coming into the literature, for example. But I think it's worth thinking about that we do have a huge, unparalleled in many ways, data set at our disposal. If you conceive of the published literature as the database, and what we are currently lacking are the data analytical and science capabilities to effectively interrogate it and write the SQL statements against it that we've been dreaming of for so long. And I think we're basically going to be there quickly, and this is a good opportunity to really close that gap between data producers and data consumers, and allow, frankly, the domain scientists like me, who spend too much time on data compilation, to get back at the job that's at hand, and that is creating new data sets from the field, because no matter what, that's going to be a priority. Thanks.
Let's give Shannon a round of applause for that. Very well said.
Last
Hey,
question.
Carol.
Hi.
Carol Palmer, University of Washington.
Thanks for all of that, Peter. And I also wanted to comment on the producer-consumer, because I've been sort of obsessed with that as well over the years, and especially in terms of small data, but also this idea of knowledge, information, and data, which is very much part of information science. And not forgetting, I guess, as we move data across disciplines, how much common knowledge we can't assume, especially in small science, and how much of that knowledge has to come forward. And so investing in that analytical potential and the reuse potential of data is a huge part of this whole enterprise.
Thank you. I agree, of course.
Our last question.
Okay.
Thank you, Dr. Fox.
Esri to possibly become a lighthouse project in the future and to move forward in collaboration with industry. And given that this is International World Oceans Month, with International World Ocean Day on Friday, I wanted to share this example as well. There's an AI for conservation effort going on in the Nature Conservancy, and they are working with the same AI for Earth program. They are reconfiguring their natural solutions toolkit for conservation, decision support, resource management, coastal resiliency into the artificial intelligence world, taking advantage of machine learning tools that are being provisioned here. This is their Mapping Ocean Wealth Explorer, which will be part of this transition. The Mapping Ocean Wealth Explorer is very interesting because it focuses on the value of coral reefs, particularly in terms of tourism. So it's showing you here actually what the dollar amount is in terms of reefs used for tourism throughout this part of the Pacific. So I really wanted to show you some practical examples of what's happening in the artificial intelligence world with machine learning as the engine of that. At Esri, we have a GitHub repo which has our code, our use cases, data sets, examples. In fact, Esri is a private software development company, actually has about 250 open source projects going on right now. So open source is very, very powerful, especially if it's combined with some of the more traditional approaches. If you're interested in more information, you can get these slides at this particular URL to download my speaker notes, additional websites that you can go to, again, especially if you're a student or a postdoc. And I've been pleased to give this presentation as Esri's chief scientist, but the credit for a lot of this development work goes to Omar Mayer, who is our practice lead for advanced analytics at Esri, as well as Lucas Joppa, who is the chief environmental scientist at Microsoft. And we are loving this collaboration and including universities and nonprofits, and we would love to welcome any of you into our world as well. So thank you very much.
Questions?
I'm Karen Lloyd, University of Tennessee. I gave a talk to a amateur astronomy group recently, and they said, we've got these apps on our iPhones that we can hold up to the sky and see all the stars. When are you going to have an app so we can point it down and see what's underneath our feet?
Oh.
And now I really want it.
Yeah.
So how close are we to having such a thing?
So we're getting pretty close. The desktop app that I showed at the beginning, my first slide, that's being transitioned now. That is actually something that you can build on your own called Web App Builder if you've got your own data. So what we are moving to now is empowering users to build their own apps because they've got their own knowledge of data, they've got their own data, and so we could work with you on building that yourself.
Contact you.
Sure. Okay, ROCKD.
Connected to the literature, GeoDeep Dive.
All right, GeoDeep Dive. That is awesome as well.
Well, I have a question. I'm currently working on a remote sensing project. I'm wondering about your GitHub repository. What is the scope of the data sets that are open data sets that are available?
Oh, that's a great question. In terms of the data sets that are available, I neglected to mention that the AI for Earth initiative is focusing on 4 areas: agriculture, water, biodiversity, and conservation. So those are the nature of the data sets that are available at that GitHub repo. And part of the AI for Earth conservation grant program actually allows organizations to get access to some of these higher resolution, more expensive data sets as well, such as the NAPE imagery.
Thank you.
Hey, Dawn, thank you. As always, great talk. The thing that I think is very impressive, which I think a lot of people in the academic community don't really realize, is the degree of collaboration and cooperation that exists among the giants in the industry. And I was wondering if you could do you know of others at this level that provide substantial resources and capabilities that we're just not tapping into? Can you think of any others that might be worth mentioning?
Well, Google has always been very proactive in this area, and they have their Summer of Code and different kinds of conservation programs. I don't know as much about what's going on with these other programs in detail, but in terms of Microsoft and Esri teaming together, that's pretty big in our space. And we offer trainings. We have specialist conferences for scientists at Esri. There are about 90 PhD level scientists who are working at our company. So this is, I think we are fostering perhaps a new kind of data scientist where data scientists are actually domain scientists. And then so Ed is a wonderful example, an oceanographer who has trained himself and who has worked with the field of data science to now move into that realm. There's also the Open Cloud Consortium, which a lot of people may not be familiar with. The Open Cloud Consortium is a wonderful, is my time up? is a wonderful consortium of universities that have been working with NOAA, as well as with Amazon, Microsoft, IBM, Google. They call them the Amigos, on their big data initiative to help NOAA get their considerable store of data, particularly their weather data, out to the public.
Further questions? Thank you.
Maybe it's a good time to end with the construction. Thank you.
Please thank you.
Here in geobiology and biogeochemistry at the University of St. Andrews, where she is with the School of Earth and Environmental Sciences. And you're going to then introduce our first speaker of this next session.
Thanks, Bob, and welcome to the last session of the morning. We are going to build on these amazing sort of disciplinary talks that we had and discussions we had yesterday and start linking data from geo and bio. And so our first speaker is going to do this from the biological side, Donato Giovanelli, who is a microbiologist and a research fellow at Rutgers and their Earth Life Sciences Institute in Tokyo. And I will introduce him. He's going to talk about linking microbial metagenomics and environments.
Thank you, Aubrey, for the introduction, and thank you, everyone, for coming to the 4D workshop. I'm a microbiologist. I'm interested in extreme environment, and I'm very interested in the way geosphere and biosphere have been interacting over time. My main interest is how life can influence large-scale processes, both ecologically and through time. Today, I'll speak a little bit. I've been tasked with showing you the current state of how we can link metagenomic, but microbial data overall with environmental data out there. And during the talk, I'll talk a little bit why we're doing this. And I'll make a few examples from my own work and recent literature of what we can get out of the integration between microbial and environmental data. And also speak a little bit about the current status of the resources out there to do this, because we recently went into very optimistic about the amount of data present, and it turns out that things are not that clear in some respects. And throughout the entire talk, I'll talk a little bit about some challenges, but many opportunities that we have and that we could tackle together in this initiative. But since we have a very diverse audience, I thought I'd start a little bit broad, and so bear with me for a few slides if I say things you already know about why we should do this. The holy grail of microbial ecology is actually to integrate information and understand the relationship between microbes and their environment. Now, this can be done at a multitude of scales. We can do it on the scale of microbes growing on a single grain or a single crystal of a mineral, or we can do it at the planetary scale. Understanding how microbes interact with their environment is very important. We all know that microbes have been around for the majority of the history of our planet, and they control the majority of the bio in biogeochemical cycling. So understanding how biology has influenced and interacted with the environment and the planet over time is very important. Now, in my field, the de facto standard for doing this at the environmental level is using metagenomic. Now, this is a beautiful picture from NASA satellite of London. This is the city of London at night. Doing metagenomic in the environment is like looking at the city from very high, collecting all the population inside the city, grinding that up into a big grinder, and trying to understand what their relationship is to each other and what they do as a job. That's essentially what we're doing with metagenomic. We're picking up giant communities from the top, which we know nothing, grinding them up and trying to reconstruct how they're related to each other and what's their function in the city. Now, in doing this, having information like what size of the city it is it a coastal city? Has it a river in it? Is it a main center? It gives you a lot of information together with understanding what's the job of the people in it. And in the same way, when we use metagenomic and other type of microbial data from the environment, be it either the bottom of the ocean or the gut of humans, it's important to have environmental context around it. Once we start to link in a systematic way microbial data and environmental context, we can do all sorts of things. And I'll use here some very recent publication to show you what we can do. For example, we can look at the distribution of microbes. Delgado Baquerizo and colleagues collected microbial data for about 270 soil locations in 6 continents. And they realized that there are relatively few few microbial groups that co-occur everywhere. And those cluster according to some ecological characteristic parameters. For example, high pH cluster, the high pH organisms, they consistently cluster together versus low pH organisms. And that these can be correlated with some environmental parameters. Once you have these, you can go on and make maps like this, or prediction of the occurrence of some of the clusters on the planet, which is very powerful. On the other side, we could look, for example, at the evolution of adaptation. For example, Daniel Coleman, Everett Schock, Eric Boyd, and colleagues, they look at the evolution of acidophily, the ability of some microbes to grow a pH of 3 or lower. They sample a number of Yellowstone hot springs. You can see here the space of pH versus temperature of Yellowstone hot spring, and all the black dots are the one they sampled. And they show that preferentially in the pool there are low pH. Archaea, this colored tail color is the relationship between bacteria to archaea. They're actually higher, they dominate the environment. They went a step further and they annotated all the available archaeal genome with information about optimal growth temperature, optimum pH, and their ability to use or not use oxygen. And as you can see here, once you go below a certain optimum pH, all the isolate, irrespective of temperature, they're aerobes. The black circle are aerobes, the white circle are anaerobes. Up here you see the co-occurrence of both. Down here you see they're anaerobes. And they used genomic to show that the adaptation for necessary for being acidophile are actually widespread within the archaea and correspond mainly with the aerobic groups. Now, they use all the information to infer that perhaps acidophily has evolved not earlier than 0.8 giga years ago. This is because probably there was not enough oxygen to support the kind of metabolism that creates sulfuric acid that hyperacidify their own environment. There's a feedback on this. Something else we can do, instead of look for specific adaptation, is to look at the evolution of metabolism. And I know a number of people in this room are very interested in that. With Eli Moore, Paul Falkowski, Ben Jelen, and colleagues, we made a survey of all the available geochemical proxies for different metabolic pathways. And we tried to find a consensus age for each one of these. Now, we went a step forward. We took microbial data, the best estimate for the split of major microbial groups, and we tried to map the age of each metabolism with the group that are using it. Now, one thing that became apparent very quickly is that the majority of the splits in the major groups, they do not match any of the metabolic reconstruction from the geochemical proxies, suggesting either the information about when a specific metabolism emerged was lost, or perhaps that the metabolism emerged in a microbial lineages that has gone extinct. Now, these are few of the examples few of the information we can extract by coupling both microbial and environmental data. And we have few other examples outside on poster, like Rohier Brackman is showing how we can understand the evolution of metabolism at ecosystem level by coupling microbial data, genomic data, and oceanographic data. And I know there's a number of examples. One common theme among all this work is that, for example, Coleman et al., they had to manually annotate about 500 archaeal genome with physiological information. We had to manually verify the assignment of different metabolism to every phylum present in our tree. And Delgado Baquerizo and colleagues, they had to collect their own environmental data with every data, which should be standard practice, but you will be surprised how little is done. So a significant amount of manual labor went into collecting the data that is already there. And this brings me to my first good news moment. The data is there, mostly. There's a lot of data around. We live in a moment in which sequencing is becoming cheaper and cheaper and cheaper. And we heard about hyper-exponential curves. This is one of them. This is Moore law prediction for the cost of sequencing. This is the Illumina breakthrough, and that's where we're going now. This means it's getting cheaper and cheaper to produce data, but at the same time means also that we get more and more data. This is also a logarithmic scale, so this is actually increasing exponentially. This is the number of base pairs that are present in GenBank, one of the main repositories for sequencing data, and growing. So the good news is the data is there. That's a lot of it. Now, the bad news is that this data is often out of context, as I'll show you later. One thing I wanted to mention in talking about this is that biologists have been early innovators in some of these things we're talking about, like sharing data together. You may have seen this before. This is a DNA sequence. This is what we can get for a few dollars right now from virtually any environment or biological specimen. Now, the sequence down here doesn't make a whole lot of sense unless you compare it to something. You need to compare it to something of high quality. You need to compare it to something that is similar in order to get information. And biologists understood this very early. Margaret Dayoff in the 50s already started collecting the first few available sequences to start a database. The protein data bank we heard of yesterday started in the 70s, the Swiss Prot in the early 80s. By 1992, the NCBI, the American NCBI, the European EMDL, and the Japanese DDBJ, they joined forces together in the International Sequence Database Consortium to share the data archived within them and be sure that it's accessible and redundant everywhere. Now, there's a number of other databases that started after that, but one thing is that they're all many of those refer to each other, so you can move from one to the other. They're publicly available and they're free, and this is a big, big point to make. I also work in material science for other things, and I can tell you that Fourier transform infrared spectra of materials are largely behind paywall, and you need to pay a lot to get a good database to compare your sample with. So if great power comes from sharing, we need to understand that sharing in a coordinated way is a priority for us. Now, just sharing is not enough. This is, in biology, we've been very good at sharing sequencing data for a number of reasons. One of them is that at one point or another, it became mandatory. Early in the 90s, already the US Patent Office required you to deposit sequence, to publish the sequence if you were to patent something related to it. Now, these are few of the journals we use in my field, or we wish we use in my field, and you can see that all of them, they have a mandate for depositing the sequences, not just anywhere, not just to make them available. Your website is not going to cut it. I'll send it when people request. It's not good enough. They specifically tell you which repository sequences they have to go to at the moment of submission. You don't wait until it's published. This has to be available to reviewer, has to be available to everyone from moment of submission going down. Despite this, we still have problem with this. There's about 3 to 20% of the sequences that are mentioned in paper that do not appear in the database. This is only to remind us that we can come up with all the smart standards we want for sharing and doing things, but unless we enforce it on the community in one way or another, we're not going to get anywhere concrete. The example is also now the requirement from NSF and NASA to deposit the data on repositories. That's a good step forward. We should do it systematically for every type of data. Now, I told you there's a missing piece in all the data, and we learned this the hard way recently when with Lisa Worden, Shona Morrison, Anirudh, and Bob Bates, and we started what we call the Mineral Microbe Project. So I put here my naive biologist view of it. We have a geological context that is made up of a mineral inventory that is going to largely influence, the geochemistry available in the place. And these, in my view, should in turn influence what's the microbial function available there. To do this, we turned to one of the largest databases that is used for environmental things, which is the DOE IMG database, which you can see is a pretty big database. It's got 10 to the 13 base pair inside, about 17,000 metagenome, 90,000 projects overall. Is a huge database. We use this also because the IMG was designed to have contextual data embedded in it, things like latitude, longitude, temperature, and so on. We started working on this, and we said, wow, 17,000 metagenome, this is fantastic. We're going to have so much data to work on. And quickly we realized that things are actually, we have not been very good as biologists to collect contextual data. Once you go into IMG, you find out that out of the 17,000 metagenome available, 0% have temperature associated with it, 2% have salinity, 2% have pH. Oxygen is not even computed in most of the place. So I told myself, well, IMG is a well-established old database. The sensibility of my community, microbial community, has been changing toward the necessity of metadata or environmental data. So let's look at two initiatives that put a lot of effort into making sure that the community was sensible about collecting metadata, which are the Earth Microbiome Project, I don't know if you have heard about, and the Census of Deep Life within the Deep Carbon Observatory. I collected those data, and I realized that we're doing better, but we're not doing great yet. For example, the Earth Microbiome Project, out of 27,000 studies, 29% have temperature, 2% salinity, 17% pH. And the Census of Deep Life, 29 have temperature, 18 salinity, 21 pH. Now, this does not mean that people are just lazy. Sometimes it's difficult to get those data. Sometimes it's complex to put them inside. It's just the hard truth that if you want to use data set that have all these four attached together, it may be 5% of less of your total data. So the data is very sparse. Now, this is moving toward, the environmental side of things. So maybe we're doing better with cultured genomes and cultured relative. Recently, during my time at ELSI, with some funding from the Templeton Foundation within the EON initiative, I started collaborating with Chris Batch and Jim Cleaves that are here in the room. And we started thinking about the promiscuity of extant RNA polymerases. So this is a library of all possible scaffolds that RNA can assume within its state space. We got all the sequence of major and minor subunit of the RNA polymerase, made some modeling of the structure, and started to make docking experiments. And you can see here some of the docking versus the distance. And you can see here that our tree and our data show some pattern there. There are axes embedded here. And we started wondering, well, maybe these axes are due by being thermophile versus being mesophile or other type of physiological adaptation. So we turned to IMG again, and we have 53,000 genomes present, but look at this. 0.7 have salinity, 2% pH, and so on. The data is there because a large amount of these bacteria are pure isolates. So we could go into IJSM, the journal where this data is published, and get them one by one. And that's maybe where Shannon with GeoDeepDive can help me. We started talking about this, but right now it's simply not available in an automatic way that we can use. There's a number of reasons for which I think this is happening. And one thing is that there's a bit of a jungle, not just of data type, and I agree, we cannot expect everybody to converge into a single data type. But at the same time, there's a jungle of place where you could deposit, if you're sensitive about the issue, your data. How many of you know Pangaea? This is the popular place where to deposit environmental data in Europe. But we could go to Dryad, or we could go to the NSF one. And now, every time I'm searching for chlorophyll concentration data, I have to go to about 10 different portals to see where the data I could use is related. This is time consuming. So I think that's an opportunity for us. And I know Kristen from HERCAM was talking about meeting with the other data portal and talk about integrating together. The other reason is that the rules of engagement are not very clear. And this is true even in biology, where we've been sharing data for a long time. And this is reason for resistance from some people to releasing the raw data. It's not clear when you can use the data of someone else. It's not clear if you need to cite them and how, when they become co-author and when they're not. I think we have another opportunity here in defining rule of engagement. If we have clear rules about how the data is used, it's going to help to get more and more data out there, or at least that's what I think. Now, I didn't want it to be completely grim in my picture, quite the opposite. I think we have a large amount of opportunities we can tackle. This is the open data maturity model that has been published some time ago. For a long time, we were down here, where the status quo, the data was being present in individual PDF. I think we're moving quickly to the catalog phase. In some field, we're going to basically interactive experience. But I know that everybody's thinking about real-time data integration out there. Now, there are a number of people in the room that are helping to develop tools that help for this. And Shannon is one. The GeoDeepDive may help to move the barrier from the bottom toward the top. Adrian Hofrost, there is here, developed a tool called MetaSeq that can help you comb through GenBank based on localities, environment, special feature, so you can subset the large amount of data present. And she's now collaborating with Jana Bromberg, that we heard from on day one, that developed a new tool to annotate metagenome. Because once you get the data, you need also to analyze them in a consistent way. And getting a tool like this that allows you to do it for a large amount of data very quickly becomes very important. Now, the dream is that these two will communicate together soon, and maybe, based on location, we're also going to be able to connect to EarthChem and see what kind of geochemical data we have in the same location. On the other side, one thing we need to be changing is the culture of collecting data. For very long, we as biologists and geochemists and geologists, we've been interested in largely the same place on Earth for very long, but we've been going there at different time and sampling different things. I've been part of a project founded by the Deep Carbon Observatory and the Sloan Foundation called the Biology Myth Subduction Project, where we brought together geochemists, gas geochemists, petrologists, microbiologists, about 25 scientists from all over the world in Costa Rica to sample hot spring across the entire subduction arc. And we did this consistently by collecting synoptic collocated data for all the variables we could think at the time. Now, this is going to be hopefully soon released to the public as an open data set where we can really start to look for trends among one another. And by the way, tonight at the banquet, we're going to see a short video about this initiative, so stick around. And one other thing I've been doing on my own recently, always with some seed money from the Deep Carbon Observatory, has been leveraging some of the information are present in genomes and connecting with what you use in culture media. We have about 1,500 media recipe out there and a lot of genomes that could be mapped one-to-one to the media recipe in which they grow. A good idea for me was to let's see if there is any embedded pattern in here. Let's see if we can start to see preference of some group for using some trace element, for example, or similar. And the idea is that a bit risky at the moment. We'll see how it turns out. But the idea is that we could get, information from metagenome and metagenome reconstructed genomes out there, predict their metabolic maps, feed them into machine learning, train it on the data set of cultured media, and predict new culture recipe to try to bring into culture bacteria and prokaryotes that have not been cultured so far. So in thinking about the future, I heard a lot of the people here, and especially outside, I have to say, not a lot of the people here, talking about the data divide between data scientists and experimentalists and reductionists, or as Peter put it, between users and producers. I come from a generation that started doing microbial ecology, doing DGGE and clone libraries, is now analyzing tens of hundreds of metagenomes on a regular basis. So we are experimentalists, we are reductionists at the same time we use large data sets, we use computational tools. So I don't see this as being a divide, but actually being a circle that we need to close. You need good experimental data to connect and create the resources for data scientists, and at the same time, this creates new ideas and hypotheses that feed back into the loop. I think we need to work more to avoid to divide the camp between who's data scientist, who's not, who's experimentalist, who's not. Those are tools that my generation is using on a daily basis, and we're going to need to embrace it. Also because we need to remember, and has been said before, that once, especially in the sequencing world, where you need to compare to something to annotate your data, data annotation is only as good as the underlying database. So if you don't ensure that new information, good quality, high quality information goes into the database, you're going to end up with a bunch of junk or going the wrong direction. And I want to close off with a small list of things I think are important that we could do together. First one is raw data sharing and open science culture. That's something that is slowly changing, and I agree with the people that said before me that with the new generation this will change. Recently, a very influential person at the end of his career said that science advances one funeral at a time to remove friction. So probably we will get there soon. And I think we need to, well, actually true. I think we need to promote the collection of interdisciplinary data by getting people together in the field and working together and talking together more. We need to highlight more the advantage and opportunity of using large data approach and data science approach. Sometimes there's still kind of skepticism about what you can do when you put data together. I see it very powerful, as I show you at the start with your example. And I think we need to support the integration of data set across geobioscience discipline. This has been talked. We need to become aware that it's expensive to maintain the infrastructure, and we need to find a way to fund it. It's not enough to say that they're important. We need to do something concrete to support the people that do it. And on my side, there's a lack of framework to integrate existing sequenced environmental data. We're working with geolocated sample at the same time, but how you define data that are co-occurring. I mean, one side you have microbes at the microbe scale, on the other side you have mineralogical structure that can be small or huge. How you decide when things are overlapping or not. We need to develop innovative visualization. I don't know who in the room commented on Twitter that a 3D visualization plot is great up to a point. We need to find out something that is accessible and meaningful for everybody. And we need to develop a database. This is one of my priorities. We need a database of physiologically relevant information for all cultured and non-cultured microbial species. Because this is data that is available, it's just not machine readable right now. And I think a lot of people working on the co-evolution of geosphere and biosphere could actually benefit from it. So this is, I think, a very low-hanging fruit we could tackle. And I understand the definition of data scientist as somebody that is specialized in handling large data, but when people say I'm not a data scientist, it makes me smile a little bit because we all use data. And right now we need more and more data to do what we've been doing. I published my PhD maybe 3 or 4 years ago using 100 sequences. Today I will not be able to publish anything with 100 sequences. We need, I think, to embrace the use of data technique, large data sets, and capitalize on some of the opportunities we have in this moment. And with this, I want to thank you, all the supporters of the 4D workshop and my many collaborators. Thank you.
Excellent talk. We have some time for questions.
Richard Walrath, NASA Ames. So getting back to your metaphor about looking at London and grinding it up and looking at the genomes, which wouldn't actually tell you about what jobs, economy, and et cetera is going on in the city. So with all the focus on genomic databases, is there any thought on integrating it with proteomics databases, trying to think about, you might have the same sequence in 2 locations. Are they actually expressing the same proteins? Are they in a completely different epigenetics or metabolomics and all these other omixes out there, so to speak? And can you comment on how you can interface these together to get a broader picture?
I think that's a great question and something we've been talking about with colleagues a lot. I'm not the right person to comment on how to connect these things because I'm more a user on that side of the space. But for example, with Diana, we've been talking about in her annotation of metagenomes, can we get prediction for what kind of metal the oxidoreductases are using at the center? Can we use known PDB structure to know, map and model secondary and tertiary structure of some of the faults? It's challenging because some of the sequencing technology we use today, they give a shorter fragment of the gene, and it's not always the right place where to look for this information. But things are, technological advancement is making things easier on that side. And for example, in Costa's lab at Rutgers, we're integrating easily metagenomic and metaproteomic from the same environment. So we look at the expressed protein and we look at the genomes from an environmental sample, and that looks very promising right now. But I agree that should be the direction in which we're going, not just integrating microbial with environmental, but also among the microbial different measurements we can take.
So Carol Palmer, University of Washington. I was very interested in your comments about the amount of data collected from the same sites over time by different kinds of scientists. And we've done a little bit of work on hot springs and bringing together different scientists to try to share their data, and found that actually to facilitate that, we needed to encourage them to actually make additional measurements while they were in the field. And I'm just wondering, first sort of anchor points of changing environments. I'm just wondering if you've seen that as well in these sort of site-based locations.
Within the Deep Carbon Biology Meat Subduction project, we started off with this grand idea of let's bring a lot of very good people together that have been working in hot spring, and let's measure all we can measure. And right now we have a huge data set that is growing. It took a while to convince some people to collect data for other people or to invest time in the field, making sure that the sample was collected in a certain way instead of another. But right now that we are at the analysis stage, we know two things. The first one is we're getting a much richer picture than we would expect. So even the skeptics or the pseudo-skeptic in the group that were not too sure why we're doing this together, they're now seeing the power of collecting data together. And we also learned that we didn't plan well enough in advance. We would like to collect even more data next time in the field, because right now we have still an incomplete picture. We know we're hinting in something good, there's something missing there. As far as putting together previously collected data, it becomes difficult. We see a highly dynamic environment in hot spring where, for example, rainfall or even time of the day with evaporation can change a lot. So retrospectively, mixing data that has been collected different years at different points of the pool becomes complex. Now, I do believe that error may average out if the data set is big enough, but I'm not sure about that. That's something we're going to need to test.
Okay, in the interest of time, I think we need to move on. Thank you for that.
Thank you.
Okay, and our next speaker is going to attack this problem from the geo side of linking geo and biodata. And I'm pleased to present Tim Lyons, who is a distinguished professor of biogeochemistry at UC Riverside. And he's going to talk about linking geochemistry and biological evolution in deep time.
Thanks a lot, Aubrey, and thanks to Bob and the other organizers for this invitation. I was really honored to be included in the mix. The comment about science advancing one funeral or one death at a time reminded me, I once had a chair who said to me that, I think I was asking for a raise at the time, that the cemeteries are filled with indispensable people. So that puts it all into perspective as well. I found another job, suffice it to say, and it worked out just fine. I completely rewrote my talk last night after hearing the talks yesterday, because it occurred to me that, that there's a real opportunity to give you some perspective, at least my perspective, on where we've advanced in our understanding of early environmental evolution, and to basically put this out there as an opportunity of how the different data can be mapped on these data, which admittedly are much smaller data sets than some of the others that I've seen. But we've come a long way in the past few decades in understanding Earth history. Now, this figure here does not really reflect that, and I put it up here, I put it up here with a sense of irony because it has 88% of Earth history and this one very thin layer shown as being lifeless as well. And so this is, whether the author meant it or not, it encapsulates Darwin's dilemma that basically went from nothing to everything. But we know, and you've already heard, that there was a lot going on. We have evidence for life in oceans going back 4 billion years. And so also, just to give you a little bit of the perspective that I bring to these things, when I started graduate school, on one of the first days that I arrived, Carl Tarikian said to me that, Tim, you're wrong, you don't need two data points to define a line, all you need is one data point and a good idea. And I never really forgot that. And it doesn't mean that I didn't generate data, but I always kept that perspective. And I think that Precambrian research really invites people who are willing to step where others maybe more wisely are unwilling to go. And so I particularly enjoy it. And you'll see by the end that I've expanded this even into exoplanet research. Lots of really exciting frontiers, but I was maybe not surprised to see that the definition of oxymoron is data-rich Precambrian geochemical studies. So you won't be seeing massive amounts of data, but we have come a long way. And so these are not just so stories anymore. They're grounded in an evolving set of data with an evolvingly rigorous set of numerical models that are thrown. And really one of my great interests, not just exoplanets, but one of my great interests is trying to put genomic data and better fossil records and other indicators of the history of life on top of this. And so even before this geochemical revolution, certainly we had a sense that Earth went through major transitions in terms of its atmospheric evolution. And so there's classic work that tells us that we went from a mostly anaerobic world as manifested in iron formations and detrital pyrite to a world rich with red beds, ferric iron-dominated soils. And so in a sense, that hasn't really changed. We've done a much better job at delineating when that occurred. But they had it pretty right, people like Dick Holland and Preston Cloud and many others a long time ago. But really one of the great discoveries over the past couple of decades has been this relationship of mass-independent sulfur fractionation. And so not only can we now with some certainty say where it is, but we can say with tremendous certainty. And so it's now based on looking at the disappearance of this mass-independent fractionation, which ties to atmospheric processes favored by the absence of oxygen or very low oxygen concentrations. By moving stratigraphically and seeing the disappearance of this, we can say quite precisely that the GOE, based on this particular parameter, was between 2.3 and 2.4 billion years ago. And it's even more precise than that, and it's interfingered with glacial deposits, and we can discuss the relationship to greenhouse gas warming and how oxygenation may have decreased methane stability, et cetera. So tremendous sophistication. But for me, I think the paper that really put a lot of what I think about into motion was a landmark paper published by Don Canfield in 1998, and it built on arguments that others had made, but Don, I think, articulated it particularly well. And what Don suggested to us is that the deep ocean may have stayed oxygen deficient, anoxic, for a long time after the Great Oxidation event. And if I don't say it at the end, I'll just in case of that, I'll say it now, that the deep ocean stayed anoxic for all of the Precambrian and probably even much of the Paleozoic. So that condition was Earth's norm rather than what we experience today. And that led naturally to this sense of trying to understand the abundance of bioessential metals within oceans that were largely anoxic. And what was the nature of the anoxia, and when did the surface ocean oxygenate? And anoxia is a multifaceted term. There's iron-rich anoxia, there's sulfur-rich anoxia, there are very low oxygen conditions that are dominated by microbial processes like manganese reduction and denitrification, and they all have different manifestations for life, and they all have different geochemical expressions. And because we think as modern oceanographers, when we look back in the past, we can recognize the signals of these differences. We can nuance environmental gradients through Earth history. And so it's now a hot topic to consider these enzymatic cofactors and their distributions through time. And I have certainly joined that bandwagon along with many others in the room. But what my group is trying, and others are certainly trying to bring to this with added rigor, I think, is to try and massage out as best we can these trace metal micronutrient landscapes through time. And so in the wake of the Ambar and Knoll paper, Max Sato and colleagues published this general distribution of what metals might have been like through time, and it was based on a very, very simple assumption that before the GOE, the ocean was iron-rich, it was anoxic and dominated by ferrous iron, and we know this from the banded iron formations that are ubiquitous during this time. And then the so-called Canfield Ocean dominated the middle chapters of Earth history, and whether Don intended it or not, it generally has been assumed, or for a long time it was assumed to represent a global distribution of sulfidic conditions, which is really impossible to happen. Productivity is too low in the central gyre regions. It's really hard to support sulfate reduction in those regions, and so at best we would have had sulfidic margins. But that's not how it was treated then, and then we know sometime in the late Precambrian, oxygen increased. In fact, when that was first suggested, much of the evidence for that was the rise of animals, and then ultimately the rise of animals was attributed to the rise of oxygen. So it became very circular, and we wanted to come at these things as independently as possible. And so what we really want to do is try and, again, understand these relationships between metals and life through time. And Chris DuPont published, I think, a really seminal paper in PNAS back in 2010, where he looked at phylogenetic analysis of protein structures, and he tried to map metal utilization through time. And he tried to relate it to a very simple ocean redox model through these key intervals. And he assumed, as Sato did, an iron-rich early ocean, a sulfide-rich middle ocean, and an oxygen-rich later ocean. And he came to conclusions like low zinc availability during this time. And in this paper, he attributed delayed eukaryotic development to low zinc. Well, by looking at shales from this interval, we and others have published on this. In fact, there was plenty of zinc in the ocean during that time because of hydrothermal sourcing. So one of the key messages is to not make broad swaths of assumption over billions of years and do thermodynamic modeling and come up with your general metal distributions based on that, but to go after samples, to go after data, and to ultimately to try and bring all these things together. And so what I'll talk about for the next couple of minutes is this idea of more direct ways of tracking trace metal availability through time. And these things are predicated on pretty simple assumptions. One is that the delivery of metals to the ocean is controlled largely by the amount of oxygen in the atmosphere. These metals are associated with sulfides. And so when oxygen started to accumulate in the early ocean, the sulfides weathered on land and delivered metals to the ocean by rivers. Those metals are then transported by the rivers to the ocean. And the ultimate abundance of the metals in the ocean over geologically, biologically relevant timescales depends not only on the source term, but also how rapidly, how efficiently they are consumed into sediments. And so the sink term becomes equally important, and I show the Black Sea because it is our largest example today of an anoxic basin. It is sulfidic. The term euxinic, which I will probably use multiple times, which means anoxic and hydrogen sulfide containing, comes from the ancient name of the Black Sea, Pontus Euxinus. And so the simple idea is that if you've turned on the source term, but much of your ocean is anoxic or sulfidic, it can draw down those metals as quickly as they come in. And how much inventory you maintain in the ocean at a given time and how much you can enrich sediments at a given time is really a function of the balance between the source and sink. And so we just might be able to map the distribution of anoxic conditions or sulfidic conditions, euxinia in the ocean, and we might even be able to model concentrations of metals in the ocean from the enrichment patterns that we see in shales and iron formations and other host sediments. And so we tested this idea sort of, I know that has an earlier publication date, but we were thinking about these things really early on. And so Tom Algion and I published a paper looking at a bunch of modern euxinic environments. And what we found simply is that they were all enriched in molybdenum. Molybdenum loves sulfide. It goes from molybdate to tetrathiomolybdate. It's scavenged into organic matter and other particulates. And so it is really a euxinic proxy. And what we found is that these multiple euxinic environments all are enriched, all look euxinic, but show a wide range of concentrations as a function of molybdenum availability in the bottom waters. In this case, those bottom water molybdenum concentrations are controlled by the degree to which the basin is connected to the open ocean. But we wondered if we could do the same thing through time. Would we see varying enrichment patterns as a function of how much molybdenum was in the ocean, not just in the Black Sea versus the Cariaco Basin or Saanich Inlet? And so we boldly went this started around 2006. My former student, Clint Scott, went to the literature and he said, let's just pull all the molybdenum data from shales that we can. The problem is, and this is relevant to what we're talking about here, is that there are a large number and one type of data in particular that are necessary to support these compilations. And that is that you have to identify that that shale was deposited under euxinic conditions. Otherwise, you get crustal molybdenum concentrations. It has to be a setting like the Black Sea that can enrich in molybdenum. And then the degree to that enrichment depends on how much molybdenum is in the basin or the ocean. It was nearly impossible to find data that included all those necessary analyses. The other thing is it was nearly impossible as we started to collect our own samples to identify euxinic shales. It turns out that euxinia is actually relatively rare during this time, and this absence of data is not a reflection of our laziness. It's a reflection of the fact that most of the ocean, even during the Proterozoic, was ferruginous, iron-containing, rather than sulfidic. And so I could talk on and on about this. I could show you many different metals that show the same kind of pattern, and it's not a coincidence that they show this sort of stepped pattern that we argue for oxygenation that I'll show you in a minute. But Chris Reinhardt published, my former student now at Georgia Tech, published a really nice paper that came out in PNAS in 2013, where he used metal enrichment patterns from the mid-Proterozoic, about 1.8 to 0.8 billion years ago. He used those metal enrichment patterns to make inferences about the redox landscape, as we say, of the seafloor and the concentrations of, in this case in particular, molybdenum. And so the argument was that much of the deep ocean may have been anoxic. It becomes asymptotic here, so it's hard to know exactly. But these data are consistent with the Canfield Ocean in the sense of widespread anoxia, but actually only about 5 to 10% of the ocean was probably sulfide containing, so nothing like a global Black Sea. And what that allowed for was enrichment in molybdenum in euxinic shales, but muted enrichments. And so this is what the ocean probably looked like at that time. It was ferruginous throughout most of the deep waters, oxygen at some level that I'll talk about in a second in surface waters, and sulfidic conditions limited mostly to OMZ type, oxygen minimum zone type settings that we see today. High upwelling, high production, high rates of sulfate reduction, swamping the iron delivery from the surrounding ocean. So again, margins, productive margins, 5 to 10% of the ocean, leaving us with molybdenum concentrations based on our model about 1 to 2 orders of magnitude less than what we have in the ocean today. Single digit 5 nanomolar. Today, it's the most abundant transition metal in the ocean at around 105 nanomolar. So this certainly has interesting biological implications, for example, for nitrogenase. So now as we think about the atmosphere, once we cross the GOE, we've lost that mass-independent sulfur proxy. That goes away at about 10 to the minus 5th to 10 to the minus 7th present atmospheric level. The GOE, once we crossed that, we never had those levels again as much as we have seen in the data that are available, and there are many. And so we had to turn to another proxy that ultimately ties to our understanding of microbiology and manganese cycling and oxygen. And the long story short on this in this paper, this was really launched, this kind of work by Fry et al. In 2009. Basic idea is that chromium isotopes are fractured in soils as a function of chromium oxidation through manganese oxidation. And so that manganese oxidation, we think, ties to oxygen. You could argue, some have tried that there might be an anoxygenic phototrophic way of doing this. But the present understanding is that it requires oxygen, and then you have to be able to calculate how much oxygen is required to do that. So these are basically soil models of oxygen transport into the soil, oxidation of manganese, and then oxidation of the chromium and associated fractionation during these processes, and also how you retain or don't iron within these systems. And so long story short, what you see beautifully is the loss of mass-independent sulfur fractionation. We don't see fractionated chromium until 800 million years ago, and we have this wonderful middle chapter where our best guesses are that atmospheric oxygen was greater than 0.001% of the present atmospheric level and less than 1%, maybe less than 0.1%. And as you'll see in a second, that's much lower than people have been saying for many years. Really important biological implications. We can model these low oxygen concentrations, and so much of what we do now are ocean models, the Gini model, the new CONOPS model, and so we can look at physics, we can move nutrients through the ocean, we can understand distribution of upwelling and associated oxygen consumption, and so under these low oxygen concentrations, what we find is that oxygen is actually patchy within the ocean. So this is a zone of divergence. It's modern continental configurations, but it's the eastern equatorial Pacific on the margins of continents. So we're already setting up a heterogeneous landscape spatially for where oxygen was. But maybe even more importantly, as we know from looking at OMZs today, there's tremendous seasonal variability. So you're thinking, what could live in these oceans? What's it optimized for? What's the metal availability within this kind of landscape? And so the final one, and I'll let you read the paper. Zun Li is here. You can talk to him. It came out in Science last week. We're very proud of this because what it does is it uses iodine in carbonate rocks to try and constrain oxygen and oxygen stability in the surface ocean through time. Now, this is important because this is really where the action was, right? This is where the early eukaryotes were emerging. This is where the early animals were emerging. And the long story short on this is that for much of the Proterozoic, there was oxygen in the surface waters, but they were impacted frequently by proximal anoxic waters, maybe even sulfidic waters that were shoaling up into these shallow depths. And that story actually continues, if you believe our science paper, into the Paleozoic. So hostile environments in many respects. And so I wish I had more time to show you this, but we've been compiling all these different data. And the chromium speaks to the atmosphere, the iodine data here speak to the surface ocean, the molybdenum speaks to the deep ocean. So we're starting to get a sense of stratigraphy of redox in the world, whether it's a modern world or what some people envision for the Archean world. And I won't I'll clue you direct you to a geobiology paper that's coming out very soon where we've used zinc isotopes to track algal, more generally eukaryotic biomass production at this time. And so that turns on, as does almost everything we look at 800. So if you take one thing away from this talk, it's that the world really changed about 800 million years ago. And so we can look at this in many respects. One is that we can go beyond the simple view. This is what I was taught when I first began thinking about these things. And then a few years ago, I published this oxygen curve where we said, well, there's probably an overshoot after the GOE. There were transient oxygenation events before the GOE. And this, I just sort of said, I'm going to punt on that. And now this curve in 2.0 version of review to be submitted to Nature, as we can see whiffs here. We're less clear on whether oxygen was high or whether there was just high oxidant availability. Sulfate was very high in the ocean. A recent paper came out arguing that, and we believe that as well. And then we think there may have been transient events of oxygenation, but the baseline may have been low, and then it probably jumped up at 800, and then it probably dropped again, and there were transient events again. So the world of redox for us is that we go from one baseline with oscillation near the transition, we jump up, we go to a higher baseline with oscillation, and then we jump up, and that shouldn't be surprising, right? There are myriad controls and feedbacks associated with stabilizing these redox conditions, and we should very much expect to see variability as we go from one state to the other. And so we're mapping life on top of this, and we're looking at the distribution of eukaryotes, and this is a data set that is really ripe for future work, is trying to understand diversity patterns in acrotarchs, eukaryotic microfossils through time. And what you see in these data is a suggestion of a big jump at around 800. And so the vase-shaped microfossils appear, they're heterotrophic, these are eukaryotes preying on eukaryotes. And maybe the most important thing that is captured in this series of figures is that according to the Brock's paper, and my colleague Gordon Love would argue the same thing, the organic geochemists who I think are using the most rigorous methods, the first organic geochemical evidence for eukaryotes is around 800 million years ago. Now, that doesn't say that's when they first appeared. In fact, the fossil record goes back to 1.6, 1.7. So there's evidence for a big macroevolutionary lag. There's innovation, multicellularity is appearing, crown group eukaryotes are appearing, but the diversity seemed to be fairly low, to the point that these sterane compounds that derive from sterols that are particularly a fingerprint of eukaryotes don't appear until this much later time. So this is a great sort of flag for those of us who are compiling data and not thinking closely enough about it. If you went to the literature and you plotted up steranes, you would see records all through here. And it's using that discerning eye, using the hydropyrolysis Kerogen method, basically culling out data that are probably contamination or otherwise suspect. You actually really don't see those records until 800 million years ago. And so Greg is here and you can talk to him, but he is doing as well as anyone, I think, in his community of using, in his case, horizontal gene transfer, but omics approaches to try and tie to environmental patterns through time. And I don't know whether he even realizes this or not. I'm sure he does. He's a smart guy. But his argument for the beginning of cyanobacteria about 3 billion years ago is exactly when we argued for the beginnings, or at least the earliest record of oxygen production by cyanobacteria based on molybdenum isotopes in iron formations in South Africa. It couldn't be any different. And I'm pretty sure he didn't pin these data on our paper. If he did, he didn't cite it. I think it's just really a fortunate and maybe not fortuitous relationship. And so another way of looking at distributions of life through time, something that my group is very interested in, and Aubrey and others, is looking at the isotopic expressions. And I make this case all the time to NASA that many of the best early biosignatures that we have are isotopic. Carbon isotope evidence is the earliest evidence for autotrophy. Nitrogen isotopes are the earliest evidence for nitrogen metabolism. Sulfur isotopes. The biomarkers don't preserve in these very old rocks. And so we can infer concentrations, we can say that there's sulfide, but in so many cases, there are false positive scenarios where you can generate sulfide without involving life at all. And so the isotopes are oh so important. And the one thing that I haven't heard nearly enough about is the importance of tectonics. So if I gave a 5-minute, Peter just smiled, and he should, because if I gave a 2-minute talk, I would say that almost everything that I'm talking about is driven by first-order tectonics. It's not a coincidence that we have these big steps in oxygenation bookending the middle Proterozoic associated with supercontinent formation and breakup. They're really important in terms of organic carbon burial, nutrient cycling, and we've even made the argument that it might be difficult to be an exoplanet that doesn't have plate tectonics because of the requirement for some kind of phosphorus recycling, and plate tectonics does that really well. And so I'll end very, very quickly in this thing that we're so excited about right now. I'm leading one of the astrobiology teams, and we're taking this, what I call this remarkable catalog of alternative worlds. These are all images, pretty reasonable images of various stages in Earth history. And what we're trying to do is not find the Earth or necessarily even Earth-like planets, but what we're trying to do is understand holistically planetary systems. And I think of them as Legos. By looking at different chapters, all these different slices of Earth history, we learn the importance of plate tectonics. We learn the importance of redox in the ocean. We learn the importance of oxygen in the atmosphere. And we can take these Lego blocks, each of these important planetary parameters, and assemble them in any way we want. So for example, in computational space, which is really where we're headed with much of this, is we can take a mid-Proterozoic Earth as we know it and tidally lock it. Or we can remove the continents or put them all in a different hemisphere and understand what that means for the compositions of those atmospheres, because for the foreseeable future, the biosignatures are going to be compositions of atmospheres. And I'll end quickly with 2 really, really short examples. One point in the context of that is that there's going to be no shortage of data, right? Tests launched successfully recently. My colleague Stephen Kane calls it a fire hose of data, right? And so the challenge now is to identify the best targets and to optimize the next generation telescopes. And we're all excited about James Webb, but it's LUVOIR, HABEX, these other things that are in the planning stages, and people like us can inform decisions now that will impact the ability to look for biosignatures 20 years from now. And so one example, just using the Earth, is that in fact methane was probably a good biosignature during the Archean. Low ozone shielding, very aggressive photochemistry, the fact that we had high methane, an essential greenhouse gas in the face of a faint sun to keep the planet warm, almost certainly requires that we had large biological fluxes, but that asks the basic question of what could the geological fluxes have been at that time? What could serpentinization have done? What could processes without life have done? Probably not supported these high levels of methane, but we don't really know. In the Phanerozoic, oxygen would be detectable, and that's this gray-white boundary. But quite surprisingly, when we first began this, and I can explain this more during the question period, both methane and O2 were probably below detection using technology that we have now and in the foreseeable future for all of the mid-Proterozoic. So not only do you not have those individual biosignature gases or potential biosignature gases, but you don't have them in that famous disequilibrium that Carl Sagan launched all those years ago. The idea of having a reduced and oxidized gas in detectable abundance almost necessarily requires life-related fluxes. That didn't exist. Probably at no point in Earth history did we have that disequilibrium. One of the things that we're particularly excited about, and this is the last example, is seasonality. So realize, those of you who work on exoplanets, you know this already, but we'll be able to track exoplanets through annual cycles, through orbital cycles. We'll be able to direct image them. We'll be able to see seasonal variations. And I go home to my kids and I say, what would you look in the atmosphere for as biosignature? We understand these things. Well, they say, well, CO2 varies, right, as a function of respiration. It depends on where the continents are. Oxygen would vary in an opposite kind of way. There's methane variability. That's photochemical, but it requires biological fluxes to maintain the recovery after the photochemical destruction. And suddenly you have seasonal models that are reasonable. If with direct imaging, and if we get the UV capability on LUVOIR, we'll be able to measure ozone, which is more sensitive than O2. And so you can actually imagine a scenario in the coming decades where we could see a gas and with some degree of certainty say that life must be involved. And so I'll end there and just go ahead and thank these very generous and helpful funding sources through the years. And this is the first shout out to Agaron Institute. I think I didn't see this after any talk. The Agaron Institute, and John Abelson in particular, became very, very interested in the early beginnings of oxygenesis and its relationship to the origins of complex life, et cetera. And so they've paid for drilling, they fund postdocs. They don't solicit applications, but you want to get on their radar because they have been really supportive for many of us. Thank you.
We have time for one quick question.
Sure, Cayman Untaborn, ASU. Great talk, Tim.
Thank you.
My question is going back to your tracking biosignatures through time.
Yeah.
There are stars that are older than the sun, so how do we track evolution into the future for stars that are older than, or planets that are presumably older than 4.5 billion years?
I'm not quite sure I
Sure,
understand.
so if you go back a few slides to your...
Yeah.
With that right there. Right,
Yeah.
so TRAPPIST-1 is 8 billion years old.
Oh, right.
So the planets are probably 8 billion years old too. How do we track that post-Phanerozoic? Yeah.
Oh, well, that's a great question. That's we actually address that in our papers. So you can think of the Earth as capturing 4.5 billion years of history. So I know Mary's interested in this, and we are too. The Hadean is particularly ripe, actually, I think, for research right now because we actually know something about it through the Zircon data sets. We know that there were oceans. So we have many slices that capture that, but we can project all of these things forward because there's such a strong computational component of this. And so we have argued that CO2 seasonality is not detectable now because there's a signal-to-noise issue, right? CO2 is pretty abundant in our atmosphere, and the seasonal overprint is very small. But if you project with the brightening of our own sun and the silicate weathering feedback, which naturally should be pulling CO2 down, I think we say in the paper that something like 2 or 3 billion years from now, if there's still a planet, that the CO2 seasonality might actually be a functional biosignature. So it's all about knowing the stellar neighbor. We have good stellar models. We know what those things do. We know how they brighten and change through time. And it's understanding what the nature of your planet is, whether you have rocky surfaces or not, whether silicate weathering feedbacks apply or not. And so we're getting to those points, right? With albedo, we can make inferences about rockiness through transiting, knowing the size, and through radial velocities, getting the mass. We can get densities from that. And so you can get the glimmer record of surface oceans within these planets, and so I think that we're not narrowed to these alternative Earths, and going forward we're going to start calling it alternative worlds, because what we would like to do is exactly that. Let's project Earth forward, and let's make it a different Earth. Let's make the oceans off the continents or on the continents, something that Cinti cares a lot about. Let's remove the continents, all those things. Does that get to your point?
Yeah, absolutely.
Okay, great, thanks.
Okay, I would suggest that if you have extra questions for Tim, you can catch him at lunch. And let's thank him again for an excellent talk. Thank all of our speakers for this morning's last session.
Okay, before you run out, just a couple of things. For any of you who did not register for the banquet tonight but would like to attend, please see Jen or Michelle because we have very limited space. So we need to go ahead and get a head count on that if you're planning on coming. And so we're going to go to lunch now. If we could try to be in our breakout session rooms and ready to go at 2, that would help us stay on track. Well, Bob is saying 1:45, okay? So let's be ambitious, all right? 1:45.
Okay, let's get started with the reporting. First up, we have Paul Falkowski, who's representing groups 5A and 5B. Please.
Thank you very much. The word biology was coined by Buffon, and the word geology was coined by Lyell. And if you read Principles of Geology, which the first volume of the three, what ultimately would become 3 volumes of Principles of Geology, you would never know that biology and geology didn't co-evolve, because the way it was described is obvious that Lyell was a paleontologist, and as well as a very, very astute writer. And he actually presented the case for the coevolution of life in 1832. So coming back to this, obviously the biggest issues that have happened since 1833 and now is prior to the Phanerozoic, we had no idea what the rock record was. We had no idea that there was a time in Earth's history when there was no oxygen. We had no idea that there was a time before animals. And now that we have a very much more detailed understanding of what we don't know, it's trying to put this together in a geo-bio-coevolutionary context that has been a challenge for us, but an opportunity. So there are common themes between the geologists and the biologists. At one point, I think we would all just be calling ourselves naturalists. But chemical elements are the building blocks of minerals and life, and there are certain sets of elements that make up life. So the big six is what we call them: the hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. And of those, the one that is not a volatile is phosphorus. So it is the weathering product, obviously, which Jinha has been talking about in the Archean, and we know this for a long time. So the nitrogen cycle is coupled to the carbon cycle, which is coupled to the oxygen cycle, which is coupled to the sulfur cycle, ultimately, through electron transfer reactions. So life feeds off of redox gradients, and therefore one of the biggest effects of life in the geosphere is changing the redox chemistry, which is exactly why when Bob gave his talk the other day, or this morning, no, it was Shauna, yesterday, that we arose from before the GOE to something like 2,000 minerals to over 5,000 minerals because of the change in the oxidation state. So there is definitely an imprint of life in the mineral record, which we often don't really appreciate very much. And we have that gradient is something that is maintained by geology. It's not just there. So the availability of life's essential elements requires inputs from tectonic processes and from accretion. And early Earth, accretion probably was an important source of materials. So there are many research examples of the co-evolution of geospheres and biospheres. And actually, I don't even think of them this way. I tend to, and I think many of us in this room are starting to think of this as an Earth system science problem. So rather than just a geo problem or a bio problem, it's an Earth system science problem, because you have to have atmospheres and oceans and so on to carry these electrons around. So methane can be produced both abiogenically and biogenically. And this is an area which is a very interesting one right now. What were the sources of methane on early Earth, and what are the sources today? How did trace availability affect the evolution of metalloproteins, so trace metal availability? Most of the metalloproteins that are transferring electrons, the so-called oxidoreductases, utilize iron in a form of either iron-sulfur clusters, iron itself, or as a heme. So iron is there. They also use the second most abundant element in trace metal element that is used in metalloproteins is copper. And obviously molybdenum is used, manganese is used, and small amounts of other transition metals. Now, the ordinate that Jim Old was pointing to yesterday that's in common between the geosphere and the biosphere is redox itself. And it's very interesting and challenging in the data sets that we have to deconvolve the change in the redox state of Earth's upper rocks and sediments, and to correlate those with the inferred redox changes that occurred through the evolution of metabolism over geologic time. So this is really where we have a rich database of genes, we have a rich database of protein structures, although not for many of the organisms that are involved in the anaerobic metabolisms. That is still a bit of a void. And we have, obviously, databases of minerals through time and transition metals. And now other proxies, for example, iodine is coming into its own. And so it would become very much an opportunity to try to see the correlations between redox changes in time, which is not what biologists generally do. So we identified several needs. Requirements for geochemical data deposition, which we've discussed several times in this conference so far. Black shales are an example in the modern world of the deposition of organic matter, which leads to and allows for the rise of oxygen in the atmosphere. And what are the trace metal data within black shales? From modern black shales through black shales that we can see through geologic time. Isotopic data are always an extremely useful proxy for changes in redox states and changes in processes or convergence of processes through time. And here I would suggest that rather than treating one, we've tended in the past in geochemistry to treat one isotope at a time. So we focus on a carbon isotope in carbonates or a nitrogen isotope in organic matter. And here I would say that it would be useful to have a conversation about the interactions of isotope geochemistry in the rock record. So you're doing several isotopes at the same time in the same place and trying to understand how these processes are linked through an Earth system. Because the processes that are moving nitrogen around are almost always biologic, and they're related now. The electrons that are used to reduce nitrogen in the atmosphere are coming from organic carbon. So this is a process where photosynthesis, not directly but indirectly, is providing the energy for nitrogen fixation, and then nitrogen that is fixed can be oxidized by molecular oxygen, and only in the presence of molecular oxygen. And so we have a cycle of elements which I think would be much more useful to scope out on geologic times using isotopic data. Obviously, we'd like all of these data to be in useful formats so that they're easily accessed. And then we have several other things here that we discussed, and we can discuss those later if you like. Continuing on the needs, we need an accessible and comprehensive record of geosphere evolution, which is obviously a main goal, and biosphere evolution. So we don't have a rock record for the biome. We have genomes, and we have proteins, and we have other things from which we infer an evolutionary history. And sometimes correlating that to the rock record is very challenging, but I think we're making very good progress this way. We had a very long conversation about this. Then there's a need for storage and curation of geologic materials, and we can go through several of these. In the interest of time, I'm not going to go through these, but obviously the ODP is one place which is an example of core repositories, which is easily accessed from the public through requests. Public meaning scientists. And here are the opportunities that we've identified. We linked data integration, which I've already mentioned. There are data registries, which are registries of data, which I didn't know about and Nathan didn't know about. And the idea of educating the community of these resources becomes something that's interesting for our students and our postdocs and our colleagues in our institutions. So I'm going to continue on with this and just finish this up. And what we really are looking for and searching for is evidence beyond the GOE of a coevolution of the geosphere and biosphere in earlier time and in that Paleozoic period up until the rise of animals, when we already now we can see a true fossil record of animals and subsequently later plants, land plants. We are interested in developing whole Earth systems models of the essential elements with an understanding of feedbacks between life and the Earth. And here the feedbacks are going to be driven by life-driven chemistry and the geochemistry of the planet, which is supplying materials. So that's the way I think about it. Might have other conversations about this. And trying to, as I said, map out the gradients in time and space. And beyond this, we'd like to have a database for biosignatures, which is a very rich area. Do we have positive positives? We definitely don't want positive negatives to be the only thing that we have. So if you just saw no change in the gas composition and it was just an ammonia-filled planet, that would probably be a positive negative. But we'd love to have a positive positive. Now, for years I thought oxygen, that's got to be a positive positive, but some people won't let me have that anymore. So I'd love to have this lead to that conversation beyond the fossils and for use for planetary scientists within our solar system and beyond, ultimately. We had this this morning. So that's my conversation with my group, which was a very rich one. It went for a long time on early evolution of life and what the feedbacks were between life and the geosphere. Thank you.
Thank you, Paul. We have time for questions, discussion?
Thank you.
Okay. Next up, we have slight change of program. Is Penelope Boston?
Okay.
If I'm not reading this wrong.
For number 6. Okay.
What? Yeah, see what you can do with it.
Okay, you can use this or the.
Okay. Righto. Okay, I'm going to sniffle and cough my way through this. Sarah Walker had to depart from us, so the rest of us co-chairs tried to mush our two different subgroups together into something that was at least moderately coherent for this presentation. So we were the Origins of Life folks, and we tried to focus first on questions and burning needs, with the emphasis on the questions. There is a bit of mushiness between questions and needs, and that can be tidied up as we go into the future here. One of the things that was pretty clear is that a very high-level question like what is life is a big problem. Nobody has satisfactorily sorted that out. And so the question then became, how do we bypass that uber question, what is life, and develop at least an operational definition so that we can actually function, to try to deal with data sets of interest and questions of interest. We thought a better approach was what are the minimal requirements that define life that actually would fit within that operational definition. And then this next big topic is, what can we constrain? How can we reduce the number of degrees of freedom within the system so that we can begin to rule out data not of use and questions not of use? And what do we need to constrain in order to do that? There was a lot of discussion, I think, in both groups about whether or not we can and how can we quantify the various either steps or process through the origins of life. I think most of us have a view in mind that this was a somewhat gradual process, but then the question becomes, was it a series of step functions or was it essentially a continuum? We certainly know that we have both types of progress within evolution itself. Was that also true at the origins of life time quadrant, whatever that was? Can we define the threshold of adequate molecular complexity necessary to consider something the origins of life? So how complicated does something have to be before we are going to bless it with the idea that it is a primitive life form of some sort? Very important how we couple energy to increasing information content. Are they coupled? I think the way this question is stated assumes that it is, but I think a more fundamental approach to this is it coupled to increasing information content, or are they actually separate variables that may or may not be correlated? I believe that we don't think that we know the answer to that at this point. What are the key planetary processes for the origin and evolution of life? And so this encapsulates some aspects of what was discussed by several folks in both of our groups, and that is the setting, the solar system systems approach to trying to define habitability versus habitability that's inhabited and habitability that's not inhabited, and how do we scope that out on a solar system-wide basis. My own way of expressing this is that there are probably two main categories of solar systems in the galaxy. One is a life-bearing solar system, and the other is a non-life-bearing solar system. And we only have one characterized that we know as a life-bearing solar system so far, but that may change. And the fact that our solar system bears life is means that the entire solar system is a life-bearing solar system, if that makes sense. So the entire system is involved in the production of that life, even if that life occurs on only one planet. There was a lot of discussion about what biases do we bring as living things ourselves. We're stuck on carbon because carbon is a wonderful element to actually create structural and functional molecules, and that's what we are based on. Are we stuck on that? Do we have ways to contemplate and, in fact, even interrogate whether or not there are other options for basic building blocks of a life system? And what can we predict about non-equilibrium states? It was claimed that our knowledge of non-equilibrium chemistry, which is a state in which life finds itself and uses that non-equilibrium state to actually conduct its life processes, whether that is something that we know enough about just in terms of the chemistry of that, let alone the biological component of that. Then we come to the long list of needs. We need databases to be identified which already exist, but we all acknowledge that we need to make new databases. One example, of course, was chemical reactivity. And I'm not entirely sure that I know what that means, but I guess we can imagine the propensity of different compounds to interact with each other. Is there a hierarchy? Can we use that hierarchy to actually make predictions about what a life system might evolve as if we are not a single solution ourselves, if we are not a unique solution to the problem of how do you create a biosphere. The next item, needing microbial activity fluxes at the cellular level. So a better understanding of what the leakiness, I guess, of a cell to its environment and vice versa. What are the components that go into and out of it? And certainly a lot of work has been done on that, but are there large data sets that we can tap into that actually contain that kind of data? There was acknowledgement within our group that we don't know all possible databases out there, but nobody could think of one in the larger group. Molecular modeling of small molecule catalysts. So what are their transition state geometries? And importantly, what are the biomolecule or pre-biological molecule mineral interactions? And can we develop a database or mine a database or extract a database from the existing literature that would actually fit that description? The next one, it seems very general, needing a database of chemistries that are possible. There's been quite a bit of work done, at least on a notional basis, by folks like Steve Benner and so forth, about what other types of chemistries may be possible. That can be way out stuff like silicon, but it can also be alternative nucleobases and proteins and things like that. More data on fundamental reaction information and kinetics, and with particular emphasis on negative results. Where can we exclude members of that greater set that seem to not meet whatever criteria one would bring to actually make such a data set? Text mining for non-reactivity in chemical databases. I guess that, explains it the way it is. We need databases that can do a more complete atmospheric chemistry treatment of astrobiologically significant items. So what is available in the atmospheric chemistry world at this point, and which of those databases could actually be applied to the case where origins of life processes are under consideration? What are the relevant early Earth conditions? A number of people are working on different aspects of that, not the least of which being, of course, Tim Lyons with the alternate Earth work that they're doing, trying to imagine what these earlier Earth conditions were like and fill out those conditions so that one can use that as the backdrop for the origins of life processes. One call for more and better rocks from the Hadean. This is a labor-intensive field effort. We do have a number of famous rocks within that category, but it's true that the database is quite small. Certainly the work on zircons is helping to flesh that out in terms of a mineral that contains data about the early Earth, but also other rock environments have not been interrogated adequately, was the opinion of several people in our group. And then, of course, we need samples of other planets, which is easy to say and very hard to do, since we have not yet accomplished that for Mars. So I believe that is all of our specific needs. And then in the category of what are the impediments to making progress, we have a really long list here. The what? Oh, I thought I had. There, okay. All right. What are the impediments to making progress? There's lots of missing data. The missing data space is potentially very huge, and there may be methodologies that can allow us to actually investigate whether or not the distribution of the data that we have is the distribution to be expected for the missing data. And that's not necessarily the case. It may be that the distribution from the limited data that we have is quite different from what one might expect, and the way to interrogate that, of course, is to probably run simulations or something involving these data methods that we're talking about that might be able to give us insight into that. We need more examples of living systems. Okay, I'm not sure how we'll get that, except by looking at exoplanets and looking at other planets within our own solar system. We need to know more about the messy chemistry and the sloppy biology that we envision being the earliest version of our biosphere. So before the origin of life and during and shortly after. How do we link what we know about modern biology to past life and biomarkers, particularly harking back to that bias? We are highly biased because of our knowledge, and the degree to which we're educated on what we know about the modern biology may or may not be helpful. The idea of resurrecting or reconstructing or both ancestral proteins so that we can get insight into what earlier proteins may have been, even though those proteins may no longer play a role in extant life, is another example that might be pursued. The exoplanets that we are looking at now are highly biased in terms of Earth-based information for obvious reasons, but some of the questions that attend that are: what is the range of volatiles that could be expected to come from volcanoes on exoplanets within exoplanet categories of potential interest for life? And this is part of the notion that we have to develop robust suites of information about where we may have false positives. If we cannot subtract geological processes from the overall signal of an exoplanet, of course we can't make informed inferences about the presence of a biological system. Given different geotherms and atmospheric compositions, solid compositions, and in fact, even more dominant parameters like the planetary size, whether or not it has plate tectonics, et cetera, what we would expect on these other sort of Earth-like planets. Identifying not only habitats, but really micro-habitats that could have supported life, and where that life may have been actually in an environment that was preservationally competent, rather than obliterating that record. Can we identify those, and should we identify those and then try to apply that to what we can infer about the early Earth? The next one I'm particularly fond of, which is the idea of metabolic prospecting, which is looking at not only all of the major metabolic pathways and maybe even minor metabolic pathways that exist in organisms as we know them today, but also looking at other plausible metabolic pathways that have been suggested in parts of the origins of life literature that we don't seem to have representatives of. And could we subject those to these data-driven types of processes, types of analyses, and find out anything about either the uniqueness or the lack of uniqueness of the way life conducts itself here. Trying to scope out the energome, as we called it. I think it was Cynthia who said that, or somebody, yeah, it was Cynthia Parr who coined that lovely phrase, since everything is an ohm these days. I hope this is my last slide, maybe not. We need environmental constraints. What can we say about the physical geodynamical dynamics? When were continents and crust above sea level? This feeds into when did plate tectonics turn on? Other questions about whether plate tectonics were actually in the same form that we understand them now. Was it the switch is on and off and you have tectonics or you don't? Or was it, once again, a series of step functions or some kind of continuum as the planet interiorly differentiated and gave rise to the big convection cells that drive these processes? And what can our information based on Earth interpretation tell us about those processes on exoplanets? We need to be able to tailor experiments to the environment, and that has to do with almost everything that we've talked about, from biosignature detection to habitability or the lack thereof. It was pointed out by one of our members that astronomers don't hang out with geologists enough. Maybe they have slightly better grasp on the biology community, but I think Mary pointed out that maybe they need a lot more help in all different fields so that they can get a better insight into what they will actually be trying to look for as part of exoplanet studies. And then how to distinguish between biotic and abiotic signatures from afar. And this was raised in the context of exoplanets, but frankly it applies to all of astrobiology. We still have a very poorly constrained atlas in our literature, dispersed atlas in different papers about what does and does not constitute an abiotic or a biotic instantiation. Those of you who review papers probably know that there's a lot of confusion about that. So I believe that that is my end of my list. And there was a whole lot more that was said that we tried to take out duplications, but the notes that my co-chairs took were very rich. So thank you.
Thank you. So any questions or comments for Penny? Here it comes.
Not yet. Hi, Richard Walrath, NASA Ames. So as someone who started life as a synthetic chemist, I'm always a little bit surprised to not see more small molecule chemists at these kinds of things, because as you pointed out, there's a huge need for engaging that community. And I would point out that there are two excellent databases for chemical reactivity. One is called SciFinder, and the other is called Reaxys. And we can talk
Reaxys,
after.
yeah.
Yeah. And both of these are fantastic for searching organic chemistry reactions and have like millions and millions and millions of reactions, both theoretical and actual, and a lot of them have kinetics and thermodynamic data like that. So the data is out there in this case.
Good.
It's just a matter of...
So we need to add that to our database list. Yeah, Mary.
We knew about that database.
Yeah, we did.
Staff is going to tell you what else we need.
Tell me what else we need.
Well, so these databases are out there, and I also know them, but especially Reaxys is closed source, so you can't get the data.
It ain't free.
So I'm involved in one of 5 projects around this world where people have full access to the database, right? But they explicitly disallow big data approaches, so you can't take the whole database and do whatever you want with it. So that's the problem here, right? The data is out there, but it's only on a click per view basis, right? And that's unusable for the endeavor that was proposed here. Right?
So we need something big and free that we can use for any kind of project.
Yeah, and the other point is that we don't have negative reaction data in the databases, right? That's important for all the machine learning people because if we don't have negative instances, then they can't learn anything, right? So that's the problem here. We can, in a certain way, access the negative data when we mine the chemical literature. So in the chemical literature, the people in the articles write, okay, we also tried that one, but it doesn't work, right? But it doesn't end up in the databases. So if we want to have negative data, we need to take the effort and do the text mining of chemical literature and compile a database out of it.
Thank you. And I think that also applies to a lot of databases. Mary has been saying for a long time, and I agree that we need, the journal of hopeless flops and negative results and what didn't work to save us a lot of time. Not that we should never try to reproduce those things again, but so that we are wiser by the suffering of our fellows as we go into the future. Yeah.
So, Brooks Hansen from AGU, I just want to address the second to last bullet and note that we, AGU and AAS, have just received joint funding to support a series of meetings and discussions on workshops on exactly that.
Very good.
So the first one will be a union session at our fall meeting where we will be working with AAS to bring in some speakers for a union session, but if you're interested in this, please keep an eye out for that. There will be a similar session at AAS in January at their meeting where we will be bringing some of the planetary science, some of you all in this room, to the AAS meeting, and then a workshop after an exoplanet meeting next summer to actually have kind of I don't know what you want to call it, a brainstorming workshop of about 50 or 60 people to actually discuss that. And then the sessions will continue with another union session next year at our fall meeting and at AAS. So if anyone is interested in this, please reach out to me from this community. We'll have a lot more on it. We just got the funding last week or so. So Kevin Marvel and I are actually having our first meeting with a few stakeholders week after next to help plan this effort. But exactly, we feel that this is exactly needed. So my name is Brooks Hansen again, B. Hansen, B-H-A-N-S-O-N at AGU. So if anyone's interested in helping support, being involved, please reach out to me.
That's wonderful news. Thank you.
Okay, well, thank you again, Penelope. Next up, we have Eli Moore for Group 7.
All right, thanks so much. It was really a pleasure to be a part of this group. There was a lot of amazing expertise, great discussion, plenty of needs and concerns came up. So it was kind of clear that a lot of the needs and a lot of the opportunities were sort of the same thing. So a lot of that kind of got mixed up together, and then I went forward and tried to cram everything together after we combined Group 7A and B. Okay, so first topic we talked about was computing resources. So when we're thinking about the needs for exploring microbial communities, gene expression, protein expression, we're working with big metagenomic data sets. And if we're going to be looking across a wide range of data sets, a wide range of environments, we're going to be dealing with very large amounts of data, and we're going to need very big computing resources. So in some situation, it's not always clear to people who are in the microbial ecology domain how to parallelize certain types of processes. And so we need to get better linkages with bioinformaticians and computer scientists to develop new algorithms that can make these tasks more straightforward for non-computer scientists. And along those lines, repurposing generic types of tools to, again, leverage these new sophisticated parallelized algorithms. And so right now, genome sequencing, it's becoming super fast. We're getting more and more data all the time. So again, this lends towards the need for computing resources. Let's see. And so something that came up with this wealth of metagenomic data is, okay, it's a challenge for us to deal with all this data, but at the same time, it's an opportunity to start to do really big data analytics and apply types of machine learning techniques that we weren't able to do because we didn't have enough data yet. And now we have the computing resources available through different types of cloud computing that can make new types of analyses possible that we weren't able to do before. Let's see, combining big data studies. Okay, so this was along those lines. A lot of us are doing more targeted studies that are working with more specific environments and specific environmental conditions. So a challenge is that, and I'll get to this on the next slide, is getting the right metadata with the right metagenomes to work with. So in the cases where we have high level or high quality metadata, environmental data to combine with metagenomics, use those targeted studies to help inform these big data studies where we have limited or no metagenomic data, and then start to test these types of correlations that we see in the more targeted studies with the bigger data. Let's see. All right. And then, so I mentioned this just on the last slide, better metadata. So obviously, we've got a lot of cases where we have a lot of metagenomic data with not enough metadata. Some cases, and Donato talked about this a lot. We don't have temperature, we don't have pH. Sometimes we don't even have the date the sample was collected. So this needs to be, in part needs to be a culture, sociological shift to people to get over this barrier to include their all available metadata with their metagenomic studies. And we had a lot of different ideas about how to support this. Rick had the idea of presenting specific types of data sharing awards. So professional societies like AGU, AAAS can say, all right, you submitted this level of metadata, you get an annual data sharing award. And then for someone who goes above and beyond and sets up a really valuable resource that can be widely used across the community, they could have some sort of special classification. And in some cases, protocols to upload metadata are not as clear. Sometimes they're difficult. Sometimes they're just kind of voluntary. They require, some of these databases require you for limited metadata, and then they suggest if you want, you can supply the rest of the metadata, but we need to start to make those more mandatory. And let's see. Okay, and along with that, so another way to encourage this, and this is something we've been talking about a lot at USDA, Cindy Parr has been really a pioneer with this, is assigning DOIs to data sets so that people can get, if their data is being used outside of their publication, they'll get credit for it and they'll get citations. And along those lines, something that came up was, okay, let's say someone does a really giant study where they're using a wide range of data sets. We need to have a way to give credit to all the DOIs of all the different data sets that are used within that larger study. And then other people talked about, okay, yes, funding obviously is a very important driver with motivating people to submit metadata. If you take away the funding, that's definitely going to get people's attention. The example was given with some European organizations. Funding agencies will contact the university and tell them, we will pull funding, not just for this researcher, but for the whole school or for the whole department if so-and-so does not submit their metadata. And that will get the department chair's attention, and that will certainly light a fire under the researcher. Okay, further needs. Okay. Within these, when we do these types of metagenomic studies, there are certain kind of key environments that are more of interest to us, hydrothermal vents, hot springs, other types of, primitive analogs for ancient environments. And so we need to be able to create a framework for maintaining information about cultures that are significant to these types of environments and studies. So a way to make these culture studies more uniform, because these, in particular, these types of culture studies are going to be extremely important towards informing metagenomic studies in these very crucial environments. And then models and model systems. We don't always have good models or model systems to understand simple communities to work with towards building an understanding towards more complex systems. So obviously working with environmental or microbial communities is a big challenge. It's often a challenge just to culture one type of microbe from an extreme environment. And so developing widely applicable models for simple microbial communities would be a big step forward towards expanding towards more complex microbial communities, because obviously there's a lot more going on than just in the culture. There's a lot more going on in the environment than what you actually see in the culture of a single microbe. Okay, and this is something that we tried to capitalize on in the Keck project, is applying evolving network analysis techniques. And so this will be really key with metagenomics, because microbial communities are changing quickly, and there's a huge opportunity towards using the types of evolving network techniques that have been recently developed towards getting a better understanding of what's happening in these communities. And I got a lot of help from Peter Fox's group, RPI, and Anirudh Prabhu, who built different types of evolving networks that I hadn't really conceived before, and that led to some nice steps forward. So come by my poster if you want to talk more about that. But this is something that came up yesterday in the biosciences group, and this is a very big challenge, but it would be a massive step forward if we could approach this. Is find a way to detect and track either syntrophic interactions within microbial communities, quorum sensing, any types of cell-to-cell or microbe-to-microbe interactions that are going on, whether that's through metabolites, whether that's through lateral gene transfer. This will be extremely useful in terms of understanding what's going on with microbial communities. And something that came up yesterday was there could be opportunities to leverage advances in the biomedical world. So hopefully that could be an example of a step forward. And then we had a crazy thought that'll come up later from one of our group members. And then this is a need and also an opportunity with metagenomes where we don't have great metadata. Try and come up with some sort of standardized or framework towards classifying different systems. If we can classify systems in sort of a coarse way, that will give a lot more context to different metagenomes than we already have. Whether we can say, okay, this system falls into a lake system. This is a saltwater system. This is a coastal system. This is a hydrothermal vent system. That could help us a long way towards teasing out differences between microbial communities. And then opportunities. Developing databases from which we can develop hypotheses. So with this wealth of metagenomic data, we have the opportunity to really look at it in a lot of different ways, play with it in a lot of different ways, especially if we start doing things like network analysis that can help us think of new hypotheses that we can then test in the lab or in the field, or also in some cases test using geochemical proxies. And that would be a great way to link metagenomics to deep time, if we can really think of ways to use geochemical evidence. And then also large-scale text mining. So this was something I think got us all really excited yesterday with Shannon Peters' presentation, was this really large-scale text mining. And so obviously when you're doing a smaller targeted study, you need high-quality metadata. You can't have, a dozen samples with poor temperature or pH information that doesn't relate to your samples. You need it to be specific and accurate. But if you're working over large scales, if you're working on with thousands of metagenomes, perhaps there's a way to capture some of the variability with large-scale text mining. So really, I think, and folks were echoing this, we all agreed that we need to get more bioinformaticians and more computer scientists involved to work with to really flesh this out. I mean, we can all say, we want to do a big text literature dive and see how this informs metagenomics, but we actually need to take the steps to start building these tools and put it together. So now's the time to take advantage of these opportunities. Okay, and then I was glad about the last comment, combining metabolites with metagenomics. This could potentially fall into the category of understanding microbial communication interaction through linking metabolite studies with metagenomic studies. And then, and then isotopic studies. So this, and substrate studies. So this was another way we were trying to think of ways to study the behavior of microbes in extreme environments, develop more standardized approaches to use isotopic tracers or substrates that measure microbial activity to validate the presence and activity of microbes in the environment, and then possibly validate that with lab studies. And then our crazy thought that Karen Lloyd came up with was, would it be possible to build some sort of trace molecule that from one member of a microbial consortium that you could track into another microbe? So the only way it could get into the other microbe is if it was passed through some sort of metabolite transfer. So these are the types of challenges that they're very difficult, but they would really represent big steps forward, and perhaps leveraging success in the biomedical community could be a way to go. So happy to take questions.
Thank you, Eli. We have time for a few comments, questions.
Hi, Max Miller, Rutgers University. So I just want to make a brief comment to what you said in the beginning about the computational requirements we have. And I totally agree that we need to parallelize better and then that we need to make it easier to give access to this high-performance computing in a parallelized fashion. And for this reason, we developed a tool last year which allows it to very easily submit jobs to not only a local cluster, but combine resources which are available without having to deal with their environment. So it's super easy to bundle or leverage what's there and to throw your jobs on whatever clusters you have available. And so that might be interesting for some of you. And if, just get in touch with Jana Bromberg or me, and we're happy to help there.
While we have you here, so something that came up was a challenge with parallelizing genome assembly. So there may very well be straightforward ways to do that, but it's not always straightforward to or clear to microbial ecologists. So that would be an example of a useful parallelization process.
So in that case, we would really have to think about how we change the algorithm itself and not only parallelize the small subtasks.
Okay.
Hi, Eli. Sydney Parr, National Ag Library. I just wanted to respond because Eli called out the idea of assigning DOIs to data sets, and I just want to say this is not a new idea. It's been around for a little while, but just today, the Make Data Count project has released its initial implementation on Data One, and so those of you who run repositories and have been doing this, we're now in a phase where we need to implement not just assigning DOIs to things, but making sure that people are citing those DOIs and making sure that the owners of those data sets can get the information back about who's been using their data. And so this is part of making a sort of round-trip ecosystem to make sure that people get credit, and also so that we can start to prioritize which of all these large numbers of data sets are the ones that really need to be sustained for the long term for groups like yours.
Just a comment. Something I heard in your talk that I think also came up in our group was, the need actually to generate the data sets before you data mine them, right? And maybe to design experiments where you really generate big data.
So you're talking about generate data sets through text mining, or? Well, I'm actually saying
generating the data so you can text mine it.
Oh, okay.
Like, yeah, that's a
so
step.
keep doing research. Yeah. Yes. Okay. Okay. Good. Okay.
Thank you again. And then next up we have Margaret Leinen from Scripps, representing Group 8.
Thanks. Well, our group was a little different. We didn't have an organizing domain question like the coevolution of geology and biology, but we're really looking at techniques and tools themselves, critical needs and opportunities in applying new analytical and visualization methods for data-driven discovery. So we talked a little first about visualization itself and why visualization is so important to us. And the first motivation is, of course, just navigating the data space and exploring the data and using that exploration to stimulate new questions. And in the words of one of the members of our group, all of my insights come from me interpreting what the computer did with images. So I think that that means that we need to think about investment in this because of what we're going to get out of it. The second theme was multivariate data and complex systems. And almost, especially as we look at larger and larger data sets, the near impossibility of really apprehending what's in those multivariate systems or looking at complex systems without visualization. The third is interdisciplinary research. So now going beyond multivariate data from our own field, but combining that with others like bio or geo and evolution of life and so forth. And visualization makes it easier for us to go across fields. And the final, and one that we really don't want to downplay, is the importance of visualization for communicating results to each other as scientists and also to the public. And one of the members of the group highlighted the fact that I think it was, they said that there was a study published in Nature looking at citations of papers and normalizing for different fields and you know, places where there's a restriction on the number of figures. The highest cited papers are the ones with the most figures. So it kind of brings home this sense that it's those figures that we really use to abstract the result, and then that is a visual clue for us that keeps reminding us of that conclusion or that data set. So that's sort of a sense of what the opportunity is. The opportunity is doing a better job with all of those motivations. So current challenges. Here we heard a lot of frustration. First, that the available software is often very specialized and was often generated for a very specific application. And that using one visualization technique it may be very difficult to transfer that to a different application or a different use. And because of that sort of balkanization or specialization, you need to learn a lot just to try a new technique. And that means that the level, in order for us to really realize those opportunities for visualization, we need to have the level of usability become much greater. And there are many elements of what makes it more usable, and we'll come to some of those. And one person pointed out that many of us follow a scientist who used a particular visualization just because it's something that we know works, and we can go through that method and display our data that way. Not that it's the best visualization technique for our data. And so it kind of gives you a feeling for the activation energy of getting beyond something that works. Another sort of a different category of current challenges are data structure problems. We've heard a continuing theme over the last 2 days about that we often don't have the metadata, and that makes it difficult for us to determine whether the data that we're putting into the visualizations all fit together or whether there are inherent disconnects there that we haven't taken into account. The standardization of the data, and Kirsten has talked about that a lot over the last couple of days. Another example of the challenge of the data is that, and this was one of Shannon's examples, you structure the data for a specific visualization and application, and then you don't really get what you want out of that. You've put so much money, maybe money too, but time into structuring the data to get it into that visualization technique. Then if that doesn't really work for you, you've wasted all of that time and you have to go back and restructure data. So that suggested the idea that we might need some middleware in there to be able to go between a variety of different applications and the data sets. So some of those are some challenges, some limitations. This was, we talked about it in terms of going from the 2D to the giant hairball plot. And this is an ad for one of the after dinner talks tonight by Chris Johnson. He's going to explain this visualization to us. But this is a great example. If you you were trying to put two data sets together and you had to do an extraordinary amount of work to get them into the visualization, and then you got that, how would you feel? That's the challenge. Then how do we also go from 2D, from 3D to 4D to allow us to look at things in 3D and then the evolution of that with time? And so we wind up with kind of our clunky sequential maps or sequential globes or sequential diagrams. And then for some of the plots, so I remember this when I first encountered network diagrams. How do you interpret that unless you're an expert? And how do you understand what the limitations of that might be? And then another is that a lot of what we do is set on the globe. And incorporating global data on an Earth representation can be a real challenge. And finding the right architecture for a globe representation. Now, this one was very important for being able to look at the interior of the Earth. But think about what we're trying to do with inferences about the genomics or the evolution of life on that very early globe. And some of the, maybe not the interior, but maybe at least the entire crust, and understanding what's going on with that may be very important for what we're trying to say or think about with early plate tectonics and so forth. Another limitation is architecture for the representation of time that allow us to consider error in that. We're one of the few fields where we often put time on the x-axis, where the x-axis is stretchy, and that has its own challenges. So one of our group, and this was not somebody who is not an expert in visualization, this is a person that we've heard from and who had fantastic visualizations, but still said sometimes it gets so bad that I just get my niece, who is good at drawing, to draw something. So that's sort of some limitations. So what would we like to see? So first, transfer of data to the database without loss of metadata or absence of metadata. And we don't have the best ways of doing that. We tend to have systems where as soon as you try to migrate the data into the structure that you're going to use for the visualization, you lose all of the metadata. One of the set of criteria that we used for, what's the best kind of visualization, something that's fast to execute, colorful, easy to use, interactive, not platform dependent. And one of the final suggestions was made of chocolate. Just to, get a sense of, we want it all. And that's a challenge. We'd like to have visualizations that you can interact with code as well as graphical user interfaces. Otherwise, you're really restricted to what you can discover with that, and you can't manipulate that visualization very well. We heard about some experiments that are going on with hot links between data and visualization, so that you would actually be able to go in and take out parts of the data set or look at what part of the data set was in what part of the visualization. And that would also be a great opportunity. One of the things that we sat through sessions yesterday and today with all of us sometimes getting together for the first time saying, oh, try this, this is the visualization that I'm using, this is the user interface. And we don't really have many resources in this whole community that give you a guide to the different types of visualization for different types of data, and what the advantages and shortcomings of those could be, so that those of us who aren't experts in it would be able to start making some decisions about what paths we're going to go down. Some other suggestions are tools to reconstruct old data plots from pubs, virtual reality. We talked about synesthesia and, you know, the seeing music in color, and that, you know, visual reality is one example of that, but are there some tools like that that allow us to increase the dimensionality of what we can actually see in our data? And again, this should have been a quote. There's art in it and there's psychology in it, in that sense of designing what fits best with, which visualizations fit best with our data. A little bit about analytics. One of the things that our groups observed was that we've spent 2 days seeing a lot of visualizations, very few of which had error bars or uncertainty displayed in the visualization. How do we start doing that, especially for each other, to be able to get a sense of how much to trust that particular representation of the data, and the associations that we would draw from those visualizations. Also, understanding the potential for misrepresentation of color. Rainbow color distributions are inherently nonlinear in terms of the way the brain interprets the colors. Red, orange, yellow are much more intense in terms of our visibility, and therefore we draw larger distinctions between yellow and green than we do between red and orange, even if the whatever parameter space we're defining is the same distance. So we need to be thinking about that. And finally, a few recommendations. We think that it's really important, given all of these inherent things about the visualizations themselves, for our community to start interacting with the community, the visualization community. And we want to recommend some workshops to bring together the visualization folks and our domain scientists to together see what's possible, to hear a little bit about the research that's going on in visualization and see some of that in front of us, at those to have hands-on time to play with different techniques. And again, Chris Johnson's going to talk a little bit about this in his after-dinner talk. Another piece that we think we need to emphasize to funding agencies is that in light of all the work that goes into generating a visualization, it's a real cost within grants, and that we need to start putting that up front and getting funding to do visualization, which can be a significant piece of that. We can spend as much time getting a data set ready for a visualization and exploring it as we did for an airfare to come from the West Coast to the East Coast to attend this meeting. And then just a final note, after all of that, and we have the best non-hairball 3D or 4D plot, we face the tyranny of 2D PDF type publications. And so it's the challenge of representing multidimensional visualizations in a two-dimensional paper. And I included a quote from Peter Wiley of Wiley InterScience Publications, and he said the publication should, and this is his vision for publications in the future, he said the publication should be a resource guide to all of the resources that should be resulted in the intellectual insight of the author. So instead of being the thing, it should be the guide to all of the things. And I think that that's another thing we feel that we should start demanding for opportunities for publication of all of these great insights that come from visualization and analytics. That's it. This was condensed from a lot, and if any of the people that were in group A or B want to jump up and mention something that I dropped out, feel free, and Craig's right there.
So that was an incredible summary. One point I think might be worth adding to this presentation is the sort of broad approach to reproducibility and replication in the modeling and visualizations that we developed from an early stage in the process.
Yeah, and that's a mistake on my part. This whole issue of uncertainty and error is wrapped up around reproducibility as well. And we think that this is a really important issue for us to start looking at.
So you mentioned in opportunities that we want to start scaling, from two-dimensional plots more to 3- and 4-dimensional plots, and you had a really interesting bullet point, I think, that art and psychology enter into it, and it got me thinking. When we go to higher dimensions, yes, we can all of a sudden see more of the data, but also, we're 3-dimensional beings living in a 3-dimensional space, apparently. And our minds can only hold so many dimensions and so much information at once, in order for us to actually process and comprehend it. So, it makes me wonder, do we need psychologists to study, the different visualization techniques and different dimensionalities and actually figure out, what visualization techniques give us the best comprehension for different types of data sets?
It's a great point.
Maybe they are, and I don't know.
It's a great point, and we actually talked about that we need, and I should have put it in here, we need some tools for reducing the dimensionality without losing information. So, for example, if we have multivariate data, do we need to reduce that by some kind of principal components analysis or other things that give us the what a 7-dimensional plot might, but allow us to represent it in a different way. But absolutely, and what's the important part of that? What might we lose from not being able to see?
And you could miss out seeing a trend because you're too low in dimensionality, or because you're too high in dimensionality.
Yes, and that sort of was related to, how do we start developing the facility to strip out what we don't need. So not reducing the dimensionality so much as reducing what, extraneous stuff that we're throwing into this. Yeah, Dawn?
Dawn Wright, Esrian, Oregon State. A very, very nice summary, Margaret. And I think in terms of many of these points, including the point that Daniel just brought up, is that we haven't yet mentioned the other geo in terms of a discipline, one of our oldest disciplines in existence, which is geography.
Yes.
And there is a whole parallel universe there, including a field called spatial cognition, where they actually do this. They have psychologists who work with geologists and geographers and other spatial scientists on these issues. The idea of the representation of uncertainty in the visualizations, that is one of the grand challenges in geographic information science. And there's actually a program at NSF, the Geography and Regional Science Program, that funds that research. But what I'm really getting to is your call for help at workshops. There are some wonderful data visualization experts in this field who are friends of mine that I'd be happy to refer and bring them into the fold here, because similar to data science in that they are looking for very compelling problems, and they often turn to our data sets for this. So I think that would be another great meeting of the minds and a nice way to welcome yet another subdiscipline or discipline into the fold here.
Great suggestion. I'm so glad you mentioned geography and spatial cognition. The whole piece about color and misrepresentation of trends as a result of misuse of color comes exactly out of the spatial cognition community.
Penny Boston, NASA Astrobiology Institute. As I was looking at the hairballs yesterday and thinking about how I would interpret what I was seeing and realizing that I was missing a direct perception of the dimensionality and that I was still perceiving it in 2 dimensions because that's the way we display it on a screen. And one of the things about us as humans is that we're very good at integrating other senses, including auditory presentations. And it occurred to me that one could imagine a future where we would have the visual display and an auditory display coordinated so that we could take in information through at least those 2 senses. And of course, we have other senses. So you might imagine that we would even have some sort of way to feel tactile input and so forth. And I think of octopuses who sense their world with all different senses all over their bodies and stuff. And it's like, I think that even though we're very eye-minded, many people are visually impaired, and so we do have some experience with our being able to do things like fake sonar and so forth that I've seen visually impaired people sometimes develop on their own. So I think the potential for rendering this kind of multidimensional representation of data into a multi-sensory experience is not something we should rule out. I'm not sure that at my age I would be able to do that, but we're really sort of planning for the long term here. And the dimensionality flattening that goes on when you take these n-dimensional representations and just represent them in 2D seems like a terrible waste of all the work that goes into doing these.
Thank you for that. I saw a great example of using auditory information at a recent sort of presentation on new techniques, and the person took the records from all the tsunami meters for the Fukushima tsunami and sped them up. And there were about 10 of them across the Pacific, sped them up and essentially played them. And what you could absolutely hear, and it was just a profound insight that nobody had had before, was that the resonant frequency of the ocean changed after the earthquake, after the tsunami. Nobody had said anything about that before. And we never would have seen it in another way.
I'm afraid we're running a little late, and we don't want to rob the poster people too much. So if you have more questions for the speaker, please bring them up, and let's thank all our speakers. And